Hello there, and welcome to Just About Earth, where curiosity gets comfortable and science takes its time. Tonight, we're drifting gently into a version of Earth most of us never think about. It's not the Earth of maps or satellite photos, not the one with cities, forests, oceans, and weather reports. This Earth is older than history, older than bones, older even than oxygen. It's the Earth of the Archean Eon, a time so far back that the ground we live on today hadn't quite decided what it wanted to be yet. This was a world without animals, without plants, without anything you could really call familiar. The sky wasn't blue, the air wasn't safe, the sun was dimmer, days were shorter, the oceans were strange and full of elements no modern fish could survive in. And yet, this was the beginning. Not the very beginning of Earth itself, but the beginning of what we can trace. The start of the oldest rocks, the first fragments of continents, and somewhere in the chemical chaos, the earliest sparks of life. It's strange to imagine because everything we know, breathing, walking, growing food, building homes, requires an Earth that came later. But if we want to understand how we got here, we have to start back there. The Archaean wasn't quiet or simple. It was active, volcanic, unstable, and constantly reshaping itself. But that's what makes it worth exploring. It's not a peaceful memory. It's a long, slow conversation between heat, water, rock, and time. And so, wherever and whenever you're listening from, whether it's evening, early morning, or somewhere in between, take a moment to settle in. Let your thoughts slow just a bit. We're not rushing through this story. We're going to let it unfold at the pace the Earth did, slow, steady, and full of surprises. The Archaean isn't just a chapter in our planet's history. It's the first part we can still read. So let's begin there, in a time before trees, before air, before even the word Earth meant anything at all. At the start of the Archaean, the Earth was still in recovery mode. Not from civilization or climate change or asteroid strikes as we think of them today, but from its own violent birth. The planet had formed just a few 100 million years earlier, pulled together from dust and rock orbiting the young sun. It had already survived at least one catastrophic impact, the one that formed the moon, and the scars from that event still shaped the planet's surface and internal structure. Heat from these collisions, along with energy from radioactive decay, left the early Earth glowing from the inside out. By the time the Archean began, around 4 billion years ago, things were beginning to cool, but only just. The crust had started to solidify, though it wasn't the thick, stable surface we know today. Instead, it was more like a restless shell, thin in places, broken in others, constantly cracking open, and recycling itself back into the molten interior. Volcanoes weren't just scattered here and there, they were everywhere. Entire regions were dominated by volcanic activity, with magma rising from below and reshaping the landscape again and again. Above this unstable surface was an atmosphere that would have been toxic to anything alive today. It was likely dense and hot, filled with gases like carbon dioxide, methane, ammonia, and water vapour. Oxygen, the kind you're breathing right now, was almost completely absent. If you had somehow stood on the surface back then, there wouldn't be much to see beyond thick clouds and maybe the outlines of volcanic islands rising from vast dark oceans. You wouldn't last more than a few breaths, if that. Not because the planet was dead, but because it was just getting started. The oceans were already in place by the early Archean, though their origin is still debated. Some scientists believe water came from icy comets that bombarded the planet during its early history. Others think the water was always here, trapped in minerals deep inside the Earth and released slowly over time through volcanic outgassing. However it arrived, the oceans were a major part of the story from the beginning. They covered most of the surface, interrupted only by scattered volcanic landforms or fragments of early crust. And those oceans weren't the clear blue you might picture. Without oxygen, iron dissolved freely in the water, giving the seas a darker, possibly greenish or reddish hue. Combined with the hazy atmosphere and weaker sunlight, the world would have looked completely alien, dimmer, heavier, and much more volatile. Despite all that, this was a world full of chemical potential. The combination of heat, minerals, gases, and water created countless opportunities for molecules to collide, react, and evolve. Somewhere in this mix, life began. We don't know exactly when or how. The details are still uncertain and may always be. But by the middle of the Archaean, around 3.5 billion years ago, there is evidence that life was already here. Not plants or animals, not even complex cells. These were microbial organisms, single-celled and incredibly simple, but capable of growth, reproduction, and metabolism. They lived in the oceans, likely in shallow, warm environments rich in minerals and energy sources. Some clung to rocks, others floated freely, and many gathered around hydrothermal vents, where superheated water flowed from cracks in the seafloor. The earliest life may not have relied on sunlight at all. Instead, it may have used chemical energy from the Earth itself, a process known as chemosynthesis. These organisms harvested energy by breaking down hydrogen sulfide, methane, or other compounds found near underwater vents. Even today, similar ecosystems still exist at the bottom of modern oceans, home to organisms that don't need light to survive, just chemistry and time. Eventually, something remarkable happened. Some of these microbes figured out a way to use sunlight, even in the dim skies of the early Earth. This process, photosynthesis, began to reshape the entire planet. At first, it didn't produce oxygen. Early forms of photosynthesis likely used hydrogen or sulfur compounds instead. But over time, a new form emerged, oxygenic photosynthesis, carried out by organisms known as cyanobacteria. These microbes were the first to release oxygen as a byproduct of capturing sunlight. They did it slowly, and at first the oxygen didn't build up in the air. It reacted with iron dissolved in the oceans, forming rust-like minerals that sank to the seafloor. These iron-rich layers eventually became banded iron formations, geological evidence still visible today that oxygen was starting to change the chemistry of the planet. Back on the surface, the continents, or what would eventually become continents, were beginning to form. The process was uneven and slow. Instead of large land masses, there were small pieces of crust, sometimes called protocontinents, scattered like puzzle pieces not yet assembled. These fragments formed from repeated cycles of volcanic activity, cooling, and crustal recycling. As they collided and fused, they began to grow into more stable blocks, the ancient cores of today's continents, known as cratons. Cratons are among the oldest parts of Earth's crust, and many date back to the Archean. You can still find them today in places like Canada, Australia, South Africa, and parts of Scandinavia. These regions are geologically stable, having survived billions of years of tectonic activity, erosion, and metamorphism. When geologists study cratons, they're looking directly into Earth's deep past, the same surfaces that once floated in Archean seas. The movement of these crustal fragments may have resembled early plate tectonics, though the details remain a topic of research and debate. Modern plate tectonics, as we understand it, with rigid plates moving over a viscous mantle, may not have been fully active yet. The Archaean Earth was hotter, which could have made the crust more pliable, and the boundaries between plates less defined. Still, there is evidence of subduction, collision, and crustal recycling, all of which suggest a dynamic, evolving planet. Meanwhile, the length of a day on Earth was shorter than it is now, somewhere around 14 to 16 hours. That's because the Earth was spinning faster, a result of its initial momentum after formation. Over time, the Moon's gravitational pull created tidal forces that gradually slowed the rotation, but during the Archean, the world turned more quickly, and the shorter days affected everything from weather patterns to the behaviour of the tides. The Moon itself, newly formed and still moving away from the Earth, would have appeared larger in the sky. Its gravitational influence was stronger, pulling at the oceans and contributing to powerful tides, These tides may have helped mix the oceans, driving chemical reactions and supporting the development of early life. They also likely influenced erosion and sedimentation patterns along the shorelines of the Archaean seas. Magnetic fields were also already in place by this time, generated by the motion of molten iron in Earth's outer core. This magnetic field protected the planet from solar radiation, even in its early state, and may have played a crucial role in preserving the atmosphere and shielding life from harmful particles. The field wasn't as strong or as stable as it is today, but it existed, another early step in the planet's long-term habitability. One thing you wouldn't have found on this early Earth was noise, not in the way we think of it. There were no birds, no insects, no rustling leaves or animal calls. The world was quiet in a way that's difficult to imagine now. The sounds were geological, volcanic eruptions, ocean waves, the occasional cracking of crust, but not biological. Life didn't yet make a sound. That would come much later. The climate was variable, not only because of the faint young sun, but also because of shifting greenhouse gas levels. With little land to affect atmospheric circulation and no complex ecosystems to regulate the carbon cycle, temperature swings may have been more extreme both locally and globally. There's some evidence for hot conditions, but also signs that parts of the Earth may have experienced cooler climates, perhaps even limited glaciation. The balance between volcanic outgassing and chemical weathering would have played a major role in regulating the climate. As for the surface itself, it was barren. There were no plants to hold soil in place, no roots to break rocks apart, no organic material to build up over time. The landscapes were shaped entirely by wind, water, heat, and tectonics. Rain would fall, forming rivers and streams, but with nothing to slow erosion, sediments moved quickly and were deposited in layers that would eventually harden into rock. These early sedimentary rocks, when they survived, recorded the shapes of an empty world, the quiet movement of water and the slow accumulation of material on the seafloor. And yet, even in that silence, the Earth was moving forward. Every volcanic eruption, every chemical reaction in a tide pool, every new microbial lineage marked a step in a process that would eventually lead to everything we know. The air we breathe, the continents we live on, the ecosystems we depend on. The Archaean wasn't a footnote in history. It was the first sustained act of Earth's transformation, setting the stage for the world to come. We don't need to rush past it. There's still more to uncover in those oceans, in the first raindrops, in the way rock and water began their long relationship. The crust was growing, the seas were shifting, and life, however small, had made its entrance. And just ahead, the world would begin to change in ways that could no longer be reversed. The quiet beginnings were starting to echo. And from here, we can keep following where they lead. By the time early microbial life had started to find its place in the oceans, the world above the surface remained entirely inhospitable. The atmosphere of the Archean Earth was thick, alien, and completely unbreathable by modern standards. There was no oxygen to speak of, not in the air, not in the water, not even stored in minerals near the surface. It was a planet without a breath, at least not one we would recognise. The dominant gases were mostly carbon dioxide, methane and nitrogen, with smaller amounts of ammonia, hydrogen, water vapour, and perhaps some sulphur-based compounds from volcanic activity. These gases came not from biology, but from geology, released through volcanic eruptions, outgassing from the mantle, and chemical reactions at the surface. The Earth's early mantle was hotter, more chemically active, and far more prone to releasing volatile compounds. This ongoing exchange between the interior and atmosphere was one of the main drivers of the early climate. The atmosphere itself was much denser than today's. There's no exact measurement for what surface pressure was at the time, but models suggest it may have been several times higher than current levels. The high carbon dioxide content would have created a powerful greenhouse effect, necessary since the sun was still significantly dimmer. Without that insulating layer of gases, Earth's surface would have been frozen solid, Instead, the thick atmosphere trapped enough heat to keep the oceans liquid and the surface above freezing. Still, this wasn't a comfortable balance. Surface temperatures were likely higher than today's global average, though probably below the extremes reached in the previous Hadean period. Local conditions would have varied widely depending on volcanic activity, ocean circulation, and cloud cover. The sky itself may have had a different hue, possibly an orange or reddish tint due to the scattering effect of the dense, dusty atmosphere and the lack of ozone to filter sunlight. Ultraviolet radiation from the sun would have reached the surface more easily than it does now. Without an ozone layer, which today forms through interactions between oxygen and UV light, there was nothing to block the more harmful parts of the solar spectrum. Any early life that existed would have needed protection, either by living underwater, hiding in mineral crevices, or developing resistance to UV exposure through chemical means. It's one reason why deep-sea hydrothermal vents and shallow marine sediments are considered plausible cradles for early biology. They offered chemical energy and physical shelter at a time when the surface was still dangerous. The absence of oxygen also meant that there was no oxidative weathering on land, no rust-coloured soils, no oxidised minerals, and none of the geochemical processes we associate with the modern carbon and oxygen cycles. The chemical reactions that shape the land and water were fundamentally different. Iron, for example, remained dissolved in the oceans, giving the water a distinct colour and feeding into a global process that would eventually produce layered iron deposits, banded iron formations, once oxygen began to accumulate in trace amounts. This slow interaction between the atmosphere, oceans and crust began laying the groundwork for future change. Microbial life, particularly early photosynthetic organisms, would start to alter the chemistry of their environment bit by bit. Even before oxygen became a major component of the atmosphere, life was already influencing the balance of gases, cycling carbon, producing methane, and participating in reactions that subtly reshaped the world around it. Methane played a particularly interesting role. Produced by early microbes known as methanogens, this gas is a far more potent greenhouse agent than carbon dioxide. In a world with limited oxygen and abundant carbon sources, methane likely accumulated in significant quantities, reinforcing the planet's ability to retain heat. There's even some speculation that methane haze, created when methane concentrations became high enough, could have affected the climate and the appearance of the sky, similar to the way Titan, Saturn's largest moon, appears through its thick atmosphere today. Such hazes could have cooled the planet by reflecting sunlight, counteracting the warming effect of greenhouse gases. This back and forth, with warming gases and cooling haze in dynamic tension, may have created periods of climate instability, sudden shifts from warmer to cooler conditions and back again. These early feedback loops were primitive versions of the complex climate regulation systems that would evolve over billions of years, ultimately leading to the relative stability of the modern Earth. Despite its volatility, this atmosphere wasn't chaotic in the sense of constant change. It was stable on long timescales. It had patterns, cycles, and chemical pathways, just not the ones we're familiar with. It lacked oxygen, but it had its own internal logic, driven by geology, by the heat of the planet's interior, by solar radiation, and eventually by biology. The air, as it existed then, formed a system that supported the planet's chemistry and buffered its temperature, even if it couldn't support animals or plants. We sometimes think of oxygen as the most important gas for life, but for the first half of Earth's history, it was either absent or a threat. Oxygen is highly reactive. In a world without it, life evolved along different lines, using sulfur, nitrogen, or iron as electron donors and acceptors in metabolic processes. When oxygen did begin to appear, even in small amounts, it would have been toxic to many of the organisms that had adapted to an anoxic environment. What eventually became our lifeblood started out as a pollutant. This shift didn't happen all at once. For most of the Archaean, oxygen produced by photosynthetic microbes didn't reach the atmosphere in large quantities. It was absorbed by iron in the oceans, by reduced minerals on land, or simply broken down by reactions with volcanic gases. The Earth had a vast oxygen sink, a giant chemical sponge constantly soaking up the new molecule before it could accumulate in the air. It wasn't until these sinks began to fill up, late in the Archean and into the Proterozoic, that oxygen started to build in the atmosphere, leading to what's now known as the Great Oxidation Event. But that was still far ahead. For the time being, the Archean atmosphere was thick, heavy, and alien. It was more than just a blanket of gases. It was a chemical machine, one that exchanged energy, filtered radiation, and fed the first ecosystems, even if indirectly. It didn't look like ours. It didn't function like ours. But it worked. And more importantly, it left behind clues. Traces of that atmosphere survive in ancient rocks, bubbles trapped in minerals, isotopic ratios in sedimentary layers, and the chemical signatures of microbial metabolism all tell us something about what the air was made of and how it changed over time. We can't go back and sample the Archean atmosphere directly, but through geochemistry we can reconstruct parts of it, enough to get a picture, if not a full snapshot. Some of the most important evidence comes from sulfur isotopes. In the absence of oxygen, sulfur undergoes specific reactions that leave a distinct isotopic fingerprint. These signals show up in Archean rocks but disappear after oxygen levels rise, making them a reliable marker of atmospheric conditions. When we study rocks from different times and places in the Archean, we can see how the balance of gases shifted, how localized changes occurred, and how the planet moved gradually toward a new kind of atmosphere. It's easy to overlook the importance of a planet's air. We breathe it constantly, but rarely think about where it came from or how it's evolved. Yet in the Archaean, the atmosphere was not just a passive environment. It was an active participant in Earth's transformation. It controlled the temperature. It dictated the chemistry of the oceans. It set the stage for which life forms could exist and how. Without oxygen, there were limits. Large, complex life was impossible. But within those limits, the early Earth found a way to move forward. The atmosphere, strange as it was, provided the conditions for life to persist, to replicate, to innovate, and eventually to reshape the very air itself. It was a planet learning how to breathe, not with lungs or leaves, but with chemistry and time. And as the oceans began to reflect those changes, as new layers of rock started recording the first faint whispers of oxygen, the world inched closer to something new. Not a sudden leap, but a slow rebalancing. A quiet evolution, happening molecule by molecule, tide by tide. The atmosphere wouldn't transform overnight, and life wouldn't either. But the direction was set. The Earth wasn't static. It was already preparing for the next chapter, when tiny organisms would leave visible marks, and the story of life would finally break the surface. Beneath the heavy skies and quiet oceans of the Archean, the Earth's interior was anything but still. The planet was hot, not just warm, but deeply, structurally heated from the inside out. That internal heat wasn't a leftover annoyance from formation. It was a dominant force shaping every part of the planet's early behaviour. Volcanism wasn't occasional. It was constant. The surface wasn't settled. It was shifting, flexing, breaking open, and reforming again and again in cycles that defined the world. The mantle, that vast layer of rock between the crust and the core, was hotter and more mobile than it is today. Convection currents rose and fell through it with more intensity, transporting heat upward, driving volcanic activity, and recycling materials between the surface and the deep earth. The crust, where it existed, was thin and fragile by comparison. It hadn't thickened into stable land masses yet, and what solid surface there was often cracked under pressure or melted back into the mantle. This resulted in a planet with a fractured surface, a patchwork of volcanic islands, unstable continental fragments, and vast areas of open ocean. Lava flows were common, forming new crust that might last a few million years before being subducted or melted again. Entire regions could rise, cool and disappear beneath the waves, only to be replaced by new volcanic zones elsewhere. It wasn't a tidy process, it wasn't even predictable. It was molten, moody and relentless. Much of this activity happened at mid-ocean ridges and hotspots, places where magma welled up from below to create new crust. Some of these features may have resembled modern equivalents like the Mid-Atlantic Ridge or the Hawaiian hotspot, but on a scale that was more active, more frequent, and possibly more intense. Without the thick plates and well-defined boundaries of today's tectonic system, these upwellings created crustal patches that moved irregularly, collided unpredictably, and sometimes sank back into the mantle before gaining stability. Volcanoes were not just isolated cones. In many areas, entire regions were volcanic. Massive flood basalts, rift zones, or chains of submarine eruptions that built temporary islands. The eruptions themselves varied, from slow, oozing lava flows to explosive gas-charged events that released ash and gases into the thick atmosphere. These eruptions helped shape the chemistry of the air and oceans, contributing gases like carbon dioxide, sulfur dioxide, and water vapour, as well as trace elements like chlorine and fluorine that would participate in further reactions at the surface. On land, where land existed, the results were temporary. Basaltic plains formed, eroded, and reformed. Rock cooled slowly under thick atmospheres, and chemical weathering was limited by the absence of vegetation. Without roots to break apart rocks or soil to absorb water, the landscape was sculpted almost entirely by rain, tides, and gravity. Slopes collapsed, lava hardened, then cracked again. It was a dynamic, temporary, and unstable surface, one that rarely lasted long enough to become permanent. Even underwater, the planet's mood was volcanic. Hydrothermal vents dotted the seafloor, especially near spreading centres. These vents spewed mineral-rich water into the surrounding ocean, creating localised ecosystems and unique chemical environments. Today, similar vents support entire communities of life, from bacteria to tube worms, that rely on chemical energy instead of sunlight. In the Archean, such environments may have been among the most stable habitats available. Warm, protected, and rich in nutrients, offering refuge in a world otherwise dominated by heat and flux. All of this was happening under a sun that didn't shine quite the way we're used to. The sun during the Archean was about 70 to 80% as bright as it is today. It was still a young star, only a few 100 million years into its stable main sequence phase. The difference in brightness might not sound extreme, but it had significant consequences. Less solar energy reaching the Earth meant a cooler baseline temperature, unless something compensated for the shortfall. That compensation came, as mentioned earlier, from greenhouse gases, especially carbon dioxide and methane. Without them, the oceans would have frozen despite all the internal heat, but with a dense enough atmosphere, enough volcanic outgassing, and enough biological methane production, the Earth was able to maintain liquid water and a mostly temperate surface, though always at risk of tipping one direction or the other. And while the sun was dimmer overall, it was also more active in other ways. Young stars tend to produce more solar flares and ultraviolet radiation. Without an ozone layer to filter it, UV light would have struck the surface more directly, especially at higher elevations and in clear sky conditions. This created a strange contrast, a world with lower total light but higher exposure to certain harmful wavelengths. The planet was simultaneously underlit and overexposed. This faint but volatile sunlight meant that daily and seasonal rhythms were different from what we experience today. The sky may have been more often overcast, filtered through clouds and atmospheric haze. Sunlight would have reached the surface as a duller, more scattered glow, not the bright blue sky days we take for granted now. Sunrises and sunsets might have looked redder, longer, and stranger. The sky itself, in the absence of modern air composition, might have had hues that are hard to predict. with theories ranging from orange-tinted daylight to persistent high-altitude hazes that dulled everything. The length of each day, still shorter than ours, gave the sun a faster arc across the sky. Days passed more quickly, with nightfall coming sooner and mornings arriving in a tighter rhythm. The moon, still closer to Earth at this point, would have dominated the night sky, larger and more prominent than it appears today. Its tidal effects were stronger, its light more significant, and its presence more central to Earth's geophysical balance. The combined result was a world of contrasts. The Earth was constantly moving between molten instability and cooling order, between volcanic creation and erosive breakdown. The sun, though weak, pushed light and radiation into a dense and complex atmosphere. Oceans boiled near vents and cooled near shadowed shores. The land was new but rarely stable. It was a place of perpetual transition, never quite the same from 1 million years to the next, and certainly unrecognisable by modern standards. And yet, through all of this, structures began to form. Rocks hardened, islands persisted long enough to layer new sediments. Ocean chemistry began responding to biological input. The repetition of volcanic cycles created patterns in the crust. The energy released from the mantle found outlets that slowly shaped basins, ridges, and perhaps even primitive plate boundaries. Geologists studying Archean rocks can still see some of this, not in photos or direct observations of course, but in the textures, compositions and structures preserved in ancient formations, pillow basalts formed by underwater lava, komatites, rare ultramafic volcanic rocks that only formed under extremely high temperatures, point to a hotter mantle. Folded greenstone belts show regions of crust that were squeezed and buried, then exposed again by erosion or tectonic uplift. Even when the evidence is fragmented, the patterns are consistent. The Earth in the Archaean was not simply chaotic, it was in motion, under pressure, and constantly reshaping itself. Every eruption, every heat plume, every rift in the crust contributed to a long and slow process of maturation, not toward perfection, or even toward stability, but toward complexity, toward a world that could eventually support more than lava and microbes. We tend to think of modern geological activity as rare or disruptive. Earthquakes, volcanic eruptions, tectonic shifts. These events get our attention because they are uncommon in most places. But in the Archaean, they were normal. They weren't exceptions. They were the rule. The planet hadn't yet cooled enough to quiet down. Its internal engine was still revving, and the surface bore the marks of its every move. That restless energy didn't just shape the rocks. It shaped the chemistry of the atmosphere and oceans, fed the earliest forms of life, and recycled the materials that made complex life possible later. It stirred the pot, so to speak, mixing minerals, heat, and liquid water over timescales long enough for biology to take hold. And while we often celebrate the quiet stability of the present Earth, with its steady seasons, blue skies, and reliable crust, it was this earlier, more temperamental version that built the framework. A hotter Earth, a dimmer sun, and a landscape in constant revision. Molten moods that turned into mountain roots. Midnight suns that lit the path, faint but persistent. The world wouldn't stay this way forever. The crust would thicken. The atmosphere would evolve. Life would push outward and upward. But in this part of Earth's story, everything was still in flux. Not random, but not yet ordered. And somewhere in all that motion, the planet kept building. One eruption, one cooling cycle, one shifting plate at a time. The rhythm of change had begun, and it wasn't slowing down. Even in a world as volatile as the Archaean, there were moments of quiet. Not peace exactly, but shifts in rhythm. Changes in energy where something new could begin. One of those shifts came with the cooling of the atmosphere, when temperatures finally dropped enough for water vapour to condense, gather in clouds and fall from the sky. The first rain didn't arrive with ceremony. There were no plants to catch it, no soil to absorb it, no animals to scatter in its path. just volcanic rock, bare and hot, meeting water that had once been steam. The early atmosphere was saturated with vapour from constant outgassing and from the surface itself, which still radiated heat. As the planet continued to cool, that vapour condensed, eventually forming clouds thick enough to produce precipitation. This wasn't a single event. It likely happened over and over again in pulses and waves as different regions of the atmosphere passed through cycles of heating and cooling. But over time, enough rain fell yet again and again to begin filling the low points in the landscape. Depressions in the crust formed by tectonic motion or volcanic collapse began to collect runoff. The result wasn't a clean transition from dry to wet. It was more like a gradual soaking, a saturation of the surface that formed puddles, then lakes, then vast oceans. The first raindrops likely evaporated quickly, hitting hot rock and turning instantly back to steam. But as the crust cooled and stabilised, more of that water stayed liquid. Pools lingered longer, flow paths formed, and eventually the surface reached a tipping point, enough liquid water to maintain itself, recycling between sky, land and sea in something resembling a hydrological cycle. This was a major turning point, even if no one was there to witness it. Rain didn't just cool the surface, it began to shape it. The falling water eroded rock, carved channels, moved sediment and participated in chemical reactions that would define the planet's surface chemistry for billions of years. It wasn't rain in the way we think of it now. There was no soft patter on rooftops, no storm drains or rivers bordered by trees. But the physics was the same, gravity pulling condensed moisture from clouds to ground, heat driving evaporation, and pressure systems pushing moisture through the atmosphere. Rain was also part of the feedback loop that regulated temperature. As water vapour condensed, it released heat into the atmosphere, warming it slightly and affecting cloud formation. Clouds themselves reflected sunlight, contributing to cooling. And as rain fell on volcanic rocks, it began reacting with minerals, triggering chemical weathering processes that would eventually draw carbon dioxide out of the atmosphere and lock it into the crust. These weathering reactions were particularly important because they marked one of the first large-scale mechanisms by which the Earth began regulating its own climate. Volcanism pumped CO2 into the air and weathering pulled it back out. Not immediately, not evenly, but gradually. Over long timescales, this balance helped maintain conditions suitable for liquid water, even with a faint sun and an atmosphere that was still evolving. The surfaces that received the rain were mostly basaltic, dark, dense volcanic rock formed from cooled lava. These rocks had high surface temperatures and a chemical composition rich in magnesium, iron and calcium. When rain fell on them, it triggered reactions that formed clays and carbonates, altering the landscape both physically and chemically. Over time, these altered rocks contributed to the formation of sediments that settled into basins, starting the earliest geological layering processes. Rainfall also began to create mechanical erosion, not on the scale we know now, with braided rivers and canyons, but with small-scale movement, material being loosened, transported downhill, and deposited elsewhere. In this way, the first stages of sedimentary geology were born. Even in a world without soil, the water was carving, sorting, and relocating minerals. As this happened across many regions, the low-lying areas became gathering points for water. With enough accumulation, these basins turned into the first long-term bodies of water, what we might call oceans, though their boundaries were still in flux. The early oceans were likely acidic, mineral-rich, and warm, with different layers of temperature and chemistry. They weren't stagnant. They moved with tides, wind, and currents, especially as the moon, still close and influential, stirred the water with stronger gravitational pull than it exerts today. These early oceans didn't just reflect the planet's heat and light. They began to host chemistry that had nowhere else to go. Molecules suspended in rainwater, gases dissolved from the atmosphere, minerals leached from rocks, all of it ended up in the oceans, and there it mixed. Slowly, perhaps randomly at first, but with patterns that emerged over time. The oceans became a laboratory where temperature gradients, chemical gradients, and time created the conditions for increasingly complex reactions. It's in this context that life took hold. The presence of standing, circulating water made it possible for organic molecules to form, concentrate, and interact. Small-scale wet-dry cycles on land may have contributed as well. Evaporation concentrating compounds in shallow pools, rain bringing in new materials, heat driving synthesis. But the oceans were the main stage, both for the chemistry of life and for the early microbes that would evolve from it. Rain was the delivery system, the starting point for those cycles. It connected atmosphere to crust, sky to sea. Without it, water would have remained vapour, chemistry would have remained diffuse, and life would have struggled to gather the materials it needed in one place. With rain, the world entered a new phase, one where the surface could host persistent environments, not just transient reactions. And still, there was no land as we know it. The few fragments of crust that rose above the sea were barren and dark. There were no roots to hold them together, no vegetation to stabilise their surfaces. Rain falling on these islands simply ran off, picking up minerals and carrying them to the sea. Over time, this runoff changed ocean chemistry, adding calcium, silica, and other elements that would later become critical for biological processes like shell building and internal cell structure. There's some debate about how much land was exposed at this time. Some models suggest that the early Earth was almost entirely ocean-covered, with only scattered volcanic islands or small proto-continents. Others argue that larger areas of land may have existed intermittently, rising and falling with tectonic shifts. Either way, rain was part of that process, eroding highlands, depositing sediments in lowlands, and participating in the long-term cycling of materials between land and sea. Even the process of rain itself helped cool the Earth. As water condensed and fell, it carried latent heat from the atmosphere to the surface, where it could be released and radiated into space. This ongoing exchange played a role in keeping the climate within the range needed for habitability. Without rain, the Earth's surface might have remained too hot, too chaotic, or too chemically limited to support stable life. That doesn't mean early rain was gentle or predictable. Without vegetation, storm systems likely formed and dissipated quickly, driven by sharp temperature gradients between day and night, land and sea. Thunderstorms may have been common, with lightning serving as another energy source for atmospheric chemistry. Each flash delivered a jolt that could break apart molecules, reform bonds, and drive the creation of new compounds in the air and on the ground. There's evidence that such processes contributed to the prebiotic chemistry that made life possible, not just in the oceans, but in the atmosphere and on wet surfaces. The interaction of lightning, water, and gases could form amino acids, sugars, and other organic compounds. Some of these materials would have washed into the sea with the rain, where they might be taken up by evolving biological systems. The story of rain in the Archaean, then, is not just about water, it's about interaction. Rain marked the beginning of large-scale surface processes, erosion, sedimentation, chemical cycling, that continue today. It enabled life to persist and expand. It allowed the crust to communicate with the ocean, and the ocean to feed back into the air. It brought the planet's systems into connection with each other, drop by drop. And once that pattern began, it never really stopped. Rain became part of Earth's identity, not always predictable, not always the same, but always present. A constant thread running through the planet's long history, linking fire to water, gas to rock, and chemistry to biology. As the rains continued and the oceans grew deeper, the crust responded. Islands rose, sank, and rose again. Some regions began to stabilize, others fractured. And in the warm, mineral-rich waters near those shores, microbes were beginning to build something new, not just chemical networks or survival strategies, but structures, physical traces, signs that life was no longer just reacting to the world, but starting to shape it. The next quiet revolution was already underway. Even as the rains carved channels and the oceans gathered chemical memories, something deeper was shifting. Beneath the basaltic crust, the mantle continued to churn with slow, uneven energy. Heat rose in vast columns. The thin plates of crust, fractured and unstable, responded in fits and starts. There were no continents in the modern sense, no broad shelves, no sweeping mountain chains. But the pieces were there, scattered and moving in ways that hinted at something bigger to come. It wasn't continental drift, not yet. Not as we know it. The Earth's lithosphere during the Archean was hotter, thinner and more ductile. Tectonic motion existed, but it lacked the structure and predictability of the modern plate system. Instead of large, defined plates moving across a relatively rigid surface, the early crust likely fractured more easily, forming smaller blocks that moved irregularly, collided unpredictably, and sometimes simply melted back into the mantle. These blocks, the precursors to modern continents, formed from a combination of volcanic activity, crustal thickening, and repeated cycles of burial and remelting. In some areas, new crust rose from the mantle, cooled, and began to accumulate. When two such blocks collided, their edges could be crumpled and thickened, forming more stable fragments that resisted further melting. These fragments sometimes survived long enough to begin developing a kind of identity. Thicker, lighter, more chemically differentiated than the oceanic crust around them. We call these early fragments cratons. They are the oldest, most stable parts of Earth's surface, the roots of continents that would come later. Cratons formed not all at once, but gradually, through repeated episodes of crust formation, magmatic intrusion, and high-pressure metamorphism. Over time, they cooled, thickened, and became mechanically stronger. Unlike younger, more flexible crust, cratons don't subduct easily. They float higher on the mantle and resist being recycled. You can still find these ancient cratonic regions today, scattered across the globe like geologic fossils. The Canadian Shield, the Pilbara and Yilgarn blocks of Australia, the Kapval Craton in South Africa. All of them began to stabilise during the Archean. When geologists study these areas, they're looking at direct remnants of the Earth's first long-term land. The movement of these early blocks wasn't smooth. Some may have drifted apart, others collided and stuck together. The mantle heat beneath them drove episodic magmatism, large pulses of volcanic activity that built up new layers of crust. In places where the crust grew thick enough, it began to insulate itself from the heat below, cooling more slowly, resisting deformation. These regions started behaving more like continents, staying above water, enduring erosion, and forming the high points in a mostly ocean-covered world. But they weren't continents yet, not in the full sense. They didn't have fixed shapes or boundaries. They weren't permanent fixtures of the surface. Some may have lasted a few 100 million years, others only a few tens. The difference between oceanic and continental crust wasn't yet as sharp as it would become. The processes that made continental crust thicker and more buoyant, like the formation of granitic rocks, were just beginning to ramp up. Much of the Archean crust was still mafic, meaning rich in magnesium and iron. This made it denser and more prone to recycling into the mantle. Over time, through partial melting and chemical differentiation, felsic rocks began to accumulate. Rocks with more silica, lighter in colour and density, and more likely to float and persist. These felsic components are essential for building stable continental land masses. Their gradual increase marked a turning point in Earth's geological evolution. The landscape that resulted was fragmented. Islands and microcontinents rose above the waves, only to be worn down by weathering or reabsorbed by tectonic forces. Some clustered into larger land masses, others remained isolated. The view from above, if there had been one, would have shown scattered landforms in a vast ocean, with only hints of the continents we know today. Nothing was in its final place. Everything was temporary, in motion, or still deciding what direction to go. Despite their impermanence, these early land fragments began interacting with the oceans and atmosphere in important ways. Exposed rock underwent weathering, releasing ions into the water and participating in the early carbon cycle. Sediments eroded from these proto-continents settled into nearby basins, layering into formations that would eventually become the record of the Archean. In some regions, stable shells began to develop, where repeated deposition created thick successions of sedimentary and volcanic rock. These regions now appear in the geologic record as greenstone belts, sequences of metamorphosed basalt, volcanic ash, and sediment that were deposited in Archean basins, and later squeezed and folded by tectonic collisions. Greenstone belts are among the best preserved windows into the Archean Earth, providing evidence of early tectonic processes, volcanic activity, and sedimentary environments. Their formation suggests that even if full-plate tectonics hadn't yet taken shape, something like it was underway. The processes driving crust formation and movement were episodic, bursts of activity followed by quieter periods. Heat flow from the mantle may have been concentrated in plumes, driving local melting and crust formation, rather than global-scale motion. Subduction, where oceanic crust sinks back into the mantle beneath another plate, may have occurred in isolated zones rather than along continuous margins. The Earth was trying out different geological strategies, some of which would continue, others of which would fade away. At the surface, all of this movement created new environments for life. Shallow marine basins, volcanic shorelines, tidal flats, each provided different conditions for microbial growth and preservation. When land rose above the waves, it exposed new minerals, allowed new chemical reactions, and offered substrates for microbial mats. These mats, formed by communities of bacteria, began to trap and bind sediments, leaving behind layered structures that would later become stromatolites. The emergence of semi-stable land surfaces also meant new interactions with the atmosphere. Rain falling on exposed rock triggered more weathering. Runoff carried nutrients to the sea. The air, oceans, and crust were becoming more interconnected. With each cycle of erosion and deposition, new materials entered the system. Some were locked into rock, others returned to the water, where life could use them or change them. At the same time, internal processes continued reshaping the crust from below. Magma intruded into older rock. Crustal fragments sank, melted, and reformed. High temperatures and pressures created metamorphic rocks, restructured versions of earlier crust that recorded the story of their formation in mineral textures and compositions. These rocks, now found in ancient shields around the world, are among the oldest pieces of Earth still in existence. What they show is not a static picture, but a restless one. The Earth was already experimenting with continental behaviour, trying to build something that would last. Some fragments succeeded, others failed. But through all of it, the average crustal composition was changing. More silica, more aluminum, more of the elements that define continental material. The planet was slowly learning how to build land that could stay put. There's no single moment when continents began. It wasn't an event, it was a process, and one that stretched across hundreds of millions of years. The Archaean was a time of testing, assembling the pieces and beginning to move them. The motion was real but not yet refined. The fragments were mobile but not yet fully plate-bound. It was continental drift in an early experimental phase, slow, erratic, and often undone. Still, the direction was clear. Earth was building towards something more coherent. The crust was thickening. The land was lasting longer. The rocks were recording more history. And even as the continents hesitated, gathered, or dissolved, life was adapting to every shift. The oceans fed by this changing land were more chemically complex. The environments around volcanic shores and greenstone basins were richer in nutrients. The world was starting to settle just a little. Not because the heat was gone, it wasn't. Not because the crust had stopped moving, it hadn't. But because the systems were beginning to cooperate. The deep mantle, the shallow seas, the thickening crust, and the microbial biosphere were no longer acting independently. They were entangled, sharing matter and energy in cycles that grew more efficient with each iteration. And with that growing interaction came new consequences. Microbes weren't just surviving now, they were leaving behind traces, structures that could persist in the rock record, changes in the chemical composition of sediments, and in some places visible signs that life was starting to shape the surface, not just react to it. Those signs, built slowly in tidal pools and shallow seas, would mark the next step in this unfolding story. The moment when biology began to take a more visible role, not with complexity or size, but with persistence. The surface of the Earth was ready to be written on. Life had started writing. There's a tendency, when imagining volcanoes, to picture tall, snow-capped cones, maybe puffing gently at the top or spewing clouds of ash against a blue sky. But in the Archaean, volcanoes weren't landmarks. They were the background. There weren't just a few of them, and they didn't sit quietly between eruptions. They were everywhere, constant, unrelenting. The Earth's crust in this period was as much about what came out of the mantle as what managed to stay on the surface. The planet's internal heat was still immense. Radioactive decay within the Earth's interior, a process that releases energy over time, was more intense than it is now simply because more of the unstable isotopes responsible were still around. That energy had to escape, and the surface was how it did so. The result was a world in which volcanic activity was not just common, it was essential. New crust was born almost entirely through volcanism. Ocean floors spread with basaltic flows. Volcanic islands rose, collapsed, and reformed. Submarine eruptions blanketed seafloors with fresh material, layering over and over again in sequences we still find today in greenstone belts. On land, when land existed, lava reshaped the surface with each eruption. Volcanoes weren't rare disruptions. They were the default setting. Many of these eruptions didn't happen at the surface we now think of as dry land. They occurred underwater. Most of the planet was still ocean-covered, and mid-ocean ridges and volcanic arcs stretched for thousands of kilometers beneath the waves. Here, lava extruded into the surrounding water, cooling quickly into pillow basalts, rounded formations that preserved the shapes of underwater flows. These pillows still show up in ancient rocks, direct evidence that Archean volcanism happened just as often, if not more so, beneath the sea as it did above. The chemistry of these eruptions also varied. Most produced mafic lava, rich in magnesium and iron, low in silica. Mafic lava flows easily, spreads quickly, and doesn't form explosive eruptions unless gas is heavily involved. But in the Archaean, some lavas were even more unusual. One of the most distinctive volcanic rocks from this era is Stromatolites. These ultramafic rocks formed from lava that was much hotter than anything we see on the modern Earth, possibly over 1600 degrees Celsius. Stromatolites are significant because they only formed when the mantle was hot enough to produce such extreme melts. They contain high levels of magnesium and exhibit flow structures that indicate incredibly low viscosity. You won't find Stromatolites forming today. The Earth's mantle just isn't hot enough anymore. But in the Archaean, they were relatively common, marking places where deep mantle plumes reached the surface with tremendous energy. Volcanoes didn't just build crust, they altered the atmosphere. With every eruption, gases were released. Not just carbon dioxide, but also sulfur dioxide, water vapor, hydrogen sulfide, and other volatiles. These gases contributed to the planet's early climate, influencing temperature, atmospheric pressure, and even the composition of rainfall. Sulfur gases in particular had a powerful effect, forming aerosols that reflected sunlight and affected cloud formation. The balance of greenhouse gases and reflective particles created a complex, constantly shifting climate. Large-scale eruptions could cool the surface by injecting sulfur aerosols into the stratosphere. Smaller eruptions might warm it by releasing more carbon dioxide. The absence of oxygen meant that some of these gases persisted longer than they would today, participating in long-term chemical cycles that were only beginning to stabilize. Underwater, volcanic activity created hydrothermal vent systems, not just isolated chimneys but entire vent fields. These were places where seawater percolated down through hot rock, became superheated, and then rose back into the ocean, carrying dissolved minerals and chemicals. Around these vents, life flourished. Not photosynthetic life, but chemosynthetic. Microbes that use the chemical energy from reduced compounds like hydrogen sulfide to build organic molecules. These vent communities may have been among the most stable biological systems on the planet at the time. The surface was unstable, UV-bathed, and subject to constant change. But deep underwater, near a steady heat source, microbes could thrive. The energy flow from the mantle through these volcanic systems may have made life not only possible but sustainable. Volcanic islands, when they did rise above the ocean, created new environments. Their surfaces cooled quickly, but their interiors retained heat. Rainwater, falling on fresh basalt, reacted with minerals, initiating weathering processes. Erosion carried material back to the sea, enriching the surrounding waters with nutrients and altering local chemistry. These islands were temporary, but while they lasted, they added variety to the surface, high points, ridges, slopes, and basins that didn't exist in open ocean. Sometimes, these islands collided with other crustal fragments, forming larger land masses. These collisions often triggered more volcanism. Magma intruded into existing rock, creating new mineral combinations and heating the crust from below. These processes were part of the early continental growth cycle, a repeating pattern of eruption, thickening, metamorphism, and stabilization. In places where volcanic arcs formed, similar to modern island chains like Japan or the Aleutians, repeated subduction and magmatism built up significant crustal thickness. These arcs may have been among the first long-lived land regions. Their structure, formed by oceanic crust diving beneath other oceanic crust, created the kind of repeating volcanic systems that could accumulate material over long periods. And yet, none of this was permanent. Subduction often recycled crust back into the mantle. Whole volcanic provinces may have formed, grown, and vanished in less than 100 million years. The Archaean Earth was a system still trying to find equilibrium. The processes that governed it, volcanism, tectonics, erosion, were familiar in principle but different in scale, temperature and timing. Geologically, the evidence for all this comes not just from volcanic rocks, but from the metamorphic zones around them. High-grade metamorphism, where rocks are buried and altered by heat and pressure, is common in Archean terrains. It shows that volcanic regions were not only active, but also deeply affected by crustal thickening and tectonic stacking. These events produced rock textures and mineral assemblages that point directly to a hot, dynamic and constantly evolving surface. Even today, Archean volcanic rocks are among the most studied for their mineral potential. The processes that built them often concentrated valuable elements, gold, nickel, copper, in ways that modern mining operations still pursue. These economic interests drive much of the detailed research into Archean geology, helping to map out the structure of rocks that have survived billions of years of weathering and tectonic distortion. But even beyond their economic value, these volcanic systems tell us something fundamental about early Earth, that the surface we walk on now, so seemingly solid and settled, was once fluid, fiery, and under constant construction. Volcanoes weren't just a feature of the landscape, they were the architects. They helped build the first continents, contributed to the early atmosphere, sustained the first ecosystems, and participated in global cycles that would eventually lead to a planet with stable climates, protective ozone, and breathable air. And all of that began here, not in silence, but in eruption. In the roar of heat meeting rock, gas meeting ocean, and chemistry meeting biology. As the volcanic surface kept shifting, the life around it adapted. Microbes colonized new lava flows, grew in sediments formed from ash, and found niches near vents and hot springs. The Earth's surface was dangerous, but it was also rich. Each eruption, each new flow of basalt or kometite, brought more material into the cycle, more rock to weather, more nutrients to carry, more heat to harness. And gradually, in the margins between land and sea, something else began to take shape. Not just microbial mats or chemical signatures, but physical structures, traces that would last, evidence that life wasn't just surviving now, it was starting to build. And once life starts leaving marks in stone, it becomes part of the geology, not just a passenger. That's where we'll go next. The Earth we know today has a distinct palette. Blue skies, white clouds, green forests, and deep navy oceans. It's familiar, expected, even comforting. But during the Archean Eon, the colour scheme was something else entirely. The skies were not blue, the seas were not clear, the world had not yet settled into its modern aesthetic. If you could have stood on an Archean shoreline, assuming you could survive the air, what you would have seen around you might not resemble anything we associate with Earth today. Let's start with the oceans. By the Archean, water had already covered most of the Earth's surface. The seas were vast, persistent, and chemically active, but they were not the sparkling blue expanses we imagine now. The absence of oxygen in both the air and the water changed everything. In the modern ocean, oxygen interacts with iron, binding it into insoluble forms that sink to the bottom and leave the water relatively clear. In the Archean, that process hadn't begun yet. Without free oxygen, iron remained dissolved in the ocean in high concentrations. This gave the water a different appearance, likely green, possibly even close to brown in some regions, depending on the mix of metals and sediments. Iron-rich water has a greenish tint, especially when combined with other minerals. In areas near hydrothermal vents or volcanic islands, the colour may have deepened due to additional inputs like sulfur or silica. Photosynthetic organisms had already emerged by this time, including early cyanobacteria, but they had not yet transformed the chemistry of the planet. Their oxygen, produced through photosynthesis, was still being absorbed by the oceans and by iron-rich rocks. Until those sinks were saturated, the oxygen stayed locked away, and the ocean remained anoxic, a term meaning without oxygen, that defines not just biology, but the entire chemical environment. This lack of oxygen allowed for the persistence of other compounds that are short-lived in today's oceans. Hydrogen sulfide, for example, may have accumulated in certain areas, especially in deeper or poorly mixed waters. Combined with iron, this could create layers of chemically distinct water, a condition known as stratification. Surface waters, stirred by wind and sunlight, may have had a different chemistry than deeper regions fed by hydrothermal activity and sediment decay. These layers would have affected not only the colour of the ocean, but also its biological potential. Life in the surface layer would have needed to cope with UV radiation and low oxygen. Life in deeper waters would have faced high pressure, low light, and possibly toxic concentrations of sulfides. The result was a patchwork of environments, some welcoming to life, others hostile, but all interconnected. Above the ocean, the sky wasn't the deep blue we associate with a clean oxygen-rich atmosphere. That familiar colour comes from the way nitrogen and oxygen scatter sunlight, specifically blue wavelengths, through a process known as Rayleigh scattering. But in the Archean, the air was different. There was nitrogen, yes, but little to no oxygen. The atmosphere was denser, loaded with gases from volcanic outgassing, including carbon dioxide, methane, water vapour, and possibly ammonia. Methane in particular has a strong effect on how sunlight passes through the atmosphere. In high concentrations, it can create a haze, not unlike what we see on Saturn's moon Titan, that scatters light differently. Instead of blue, the dominant scattering may have favoured reddish or pinkish hues, especially at sunrise and sunset. Combined with a fainter sun and possibly high-altitude clouds or sulphur-based aerosols, the effect could have been dramatic. The term hazy applies here not just visually but chemically. The Archaean sky was a reactive environment. Sunlight striking methane could trigger photochemical reactions, breaking it apart and forming more complex hydrocarbons, some of which would condense into airborne particles, thickening the haze further. This photochemical smog would have filtered sunlight, changed the planet's albedo, and contributed to warming or cooling depending on how thick it became. That haze might have protected early life from UV radiation, acting as a kind of crude sunscreen. Without an ozone layer, which today is formed from the interaction between oxygen and UV light, the surface would have been exposed to high levels of damaging ultraviolet rays. Any shielding, even from organic haze, could have made a difference for surface-dwelling or shallow-water organisms. It's also possible that this methane haze fluctuated over time. Changes in microbial activity, tectonic events, or shifts in temperature could alter methane production or destruction, creating periods where the haze thickened or cleared. Each shift would have affected not just how the sky looked, but how much sunlight reached the surface, with potential consequences for climate, ocean chemistry, and biological productivity. The interaction between the green ocean and the pinkish sky created a world of unusual contrasts. Where today we have familiar colour boundaries, blue sky meeting blue sea, green forests stretching to grey mountains, the Archaean offered something less uniform. The sea was darker, the sky was softer or dustier, and the boundary between them may have been more diffuse, blurred by haze and humidity. In terms of temperature, the greenhouse gases in the atmosphere, mainly carbon dioxide and methane, were doing most of the work. They trapped heat and kept surface temperatures within the range needed to maintain liquid water, even with a dimmer sun. But this was not a finely tuned system. Periods of volcanic inactivity, shifts in weathering rates, or changes in biological activity could tip the balance. Cooling events may have occurred, possibly even glaciation in limited regions, though evidence for global freezing during the Archean is still debated. The point is that the climate was not fully stable. It was in development, adjusting as the planet's interior cooled, as the crust matured, and as life began to interact more deeply with its environment. The colour of the ocean, the chemistry of the air, the texture of the clouds, all of it was connected. Each piece influenced the others, sometimes subtly, sometimes profoundly. Life, at this stage, was still microscopic. It moved through this world in thin films, in suspended mats, in planktonic drifts across shallow basins. It didn't need clear skies or clean water. It needed energy, raw materials, and time. It found those in the boundary zones, near hydrothermal vents, in sunlit tidal flats, around volcanic islands, wherever gradients formed and resources moved. Even as the world around it appeared alien by modern standards, life was adapting to it, shaping it slowly in return. And though we can't see it directly, we have the rocks. Banded iron formations, which formed when the first traces of oxygen from photosynthetic microbes reacted with dissolved iron in the ocean, give us the chemical signature of a green sea turning slowly towards something new. Sulfur isotope records show the atmosphere was still anoxic but changing. Carbon isotope data hints at biological productivity increasing in certain regions, perhaps seasonally, perhaps continuously. These indirect records allow us to reconstruct a picture, not with sharp detail, but with consistency. A world where the air carried methane, the water carried iron, and the light filtered through a dusty sky. A planet that wasn't barren or dead, but unfamiliar. A working system not yet refined. And within it, biology was not just surviving. It was beginning to leave patterns. Not fossils, not yet, but influence, change. Those changes would grow. As photosynthetic microbes continued to populate shallow seas and mat-like communities began to stabilise in sediment, the oceans would begin to reflect their activity more directly. The haze in the sky would start to fade. The water would begin to change colour. The entire world, still raw and unstable, would respond. Not overnight, not loudly, but persistently. And eventually, in certain places, life would begin to build something physical. Not just molecules, but structures, traces, stacks of sediment bound together by biology, recording its presence in the most durable material Earth has to offer, stone. These would be among the first features to survive into the fossil record, visible even billions of years later. The ocean and sky had set the stage. Now life was ready to step into view. The idea of a cradle implies something gentle, something enclosed, something safe. But the Archean Earth didn't offer safety in any conventional sense. The surface was unstable, the air unbreathable, the sunlight harsh. Yet somewhere in that unstable world, life not only began, it endured. It found energy, built structure, made copies of itself, and adapted. The conditions were not ideal. They were not stable, but they were sufficient. Just enough for something to take hold and not let go. Pinpointing exactly when life began is impossible. The fossil record doesn't go back far enough, and biology leaves behind few direct traces when it exists, only as single-celled organisms drifting in the sea. But the chemical signatures in certain rocks suggest that by the mid to late Archean, over 3.5 billion years ago, life was already widespread in the oceans, already photosynthesizing in some regions, and already participating in the global cycling of carbon, nitrogen and sulfur. The earliest life wasn't made of cells in the way we think of them now. It probably began as simpler self-replicating systems, molecules that could copy themselves surrounded by membranes formed from naturally assembling lipids. These structures weren't alive in the full biological sense, but they performed the necessary functions. They grew, they divided, they competed. Over time, through mutation and selection, these proto-life forms became more complex, developing the first true cellular structures and metabolisms. The source of energy for these early systems depended on location. In deep-sea environments, hydrothermal vents offered chemical gradients, differences in temperature and composition between the surrounding water and the vent fluids. These gradients could drive the synthesis of organic molecules and provide the energy for metabolic reactions. In shallow waters, sunlight became the energy source, used first by organisms that didn't require oxygen, and later by those that began to produce it. Chemosynthesis likely came first, the ability to convert inorganic molecules like hydrogen sulfide or methane into usable energy and biomass. Microbes living near vents still do this today. They don't need sunlight. They rely instead on enzymes that strip electrons from one molecule and transfer them to another, releasing energy in the process. This kind of metabolism could operate in total darkness, in the high-pressure, mineral-rich environments of the deep ocean. Photosynthesis came later, though how much later is still debated. Some of the earliest known signs of photosynthetic activity appear in rocks dated to around 3.5 billion years ago. This early form of photosynthesis may not have produced oxygen. Instead, it may have used hydrogen sulfide or other compounds as the electron donors. Only later, with the evolution of cyanobacteria, did oxygenic photosynthesis begin. The process that splits water molecules and releases oxygen as a byproduct. That development, though slow, would eventually change the world. But at first, the oxygen produced didn't accumulate in the atmosphere. It reacted immediately with iron in the oceans, forming insoluble iron oxides that settled to the sea floor. Over time, this process created banded iron formations, layers of iron-rich rock that still appear in ancient terrains around the world. These rocks are some of the earliest large-scale biological signatures on Earth, formed not from fossils but from chemistry driven by life. Where did life actually begin? There are several candidates. Deep-sea hydrothermal vents offer one possibility: hot, mineral-rich environments where water and rock interact constantly, creating gradients and a steady flow of nutrients. Alkaline vents, in particular, provide natural proton gradients across porous rock membranes, structures not unlike the ones cells use today to generate energy. Shallow water environments offer another possibility. Tide pools and coastal flats could provide wet-dry cycles, concentrating organic molecules through evaporation and mixing them with mineral surfaces that catalyze reactions. The exposure to sunlight and other environmental stresses could have driven evolution, favouring more robust molecular systems. There's also the idea of life beginning in the subsurface, in the pores and cracks of hot rock, insulated from the surface but still connected to chemical flows. This environment offers protection from UV radiation and impact events, while still allowing interaction with water, heat and minerals. It's possible that life began in one of these environments, and then migrated to others as conditions changed. Regardless of origin, by the late Archean life had spread. It occupied a variety of niches: hydrothermal vents, tidal flats, shallow seas. Microbes grew in mats on submerged surfaces, forming layered communities that trapped sediments and created complex chemical microenvironments. These mats weren't just passive. They altered the pH of the water around them, changed redox conditions, and influenced the deposition of minerals. In some places, these microbial mats became stable enough to build physical structures. As the organisms trapped and bound sediment particles, they formed domes or layered columns. Over time, these grew into stromatolites, laminated structures that preserve the pattern of microbial growth and sediment accumulation. Some of the oldest known stromatolites date to over 3.4 billion years ago, and they appear in rock formations that were once shallow marine environments. Stromatolites are among the first visible evidence of life shaping its environment in a structured, organised way. They show that life wasn't just present, but active, building, modifying, and persisting. These weren't isolated events. Stromatolites appear in multiple locations, across different parts of the ancient world, suggesting that wherever conditions were right, life found a foothold and held on. The biological processes behind these structures also began to influence the planet more broadly. Photosynthesis, whether oxygenic or not, altered the balance of gases in the ocean. Metabolism affected the chemistry of sediments. Life was beginning to participate in feedback loops, taking in materials, processing them, and returning them in different forms. The carbon cycle, the nitrogen cycle, the sulfur cycle. All of these began to take recognizable shape during the Archaean, even if they weren't yet fully developed. There's no sharp dividing line between non-life and life, just as there's no clear boundary between simple chemistry and complex metabolism. But somewhere in this eon the shift occurred. Molecules became systems, systems became organisms, and organisms began to persist across generations, adapt to their surroundings, and influence the environment around them. The Earth was no longer just a physical system. It had become, however quietly, a biological one. That transition didn't end the chaos. The planet was still volatile. Volcanoes still erupted. The sky was still thick and strange, but now there was something new: persistence, life that could survive those changes, or at least return afterward. Communities that could regrow after disturbance, chemistry that could repeat, refine, and become more efficient with time. And over time, those systems would begin to expand. Life would move from isolated mats to larger communities. It would begin to influence the shape of coastlines, the composition of oceans, and the nature of the air above. Its fingerprints, still faint, were beginning to show up everywhere, not in bones or leaves, but in isotopes, minerals, and sediments. The cradle of life, such as it was, didn't rock gently. It was surrounded by fire, gas, and shifting tides. But it held, and as it did, it set the stage for everything that followed, not with certainty or speed, but with resilience. the resilience to persist through everything the Earth could throw at it. That would prove to be enough. Because in the long story of this planet, persistence always matters more than speed. From here, life wouldn't stay small forever. It would begin to change the very rocks it grew on, not just chemically, but visibly. And it would do so in a world still very much in flux. A world where oceans rose and fell, where land shifted underfoot, and where biology for the first time began to reshape geology. By the time microbial life had carved out a foothold in the Archean world, the planet had no shortage of places to grow. But very few of those places would seem welcoming by modern standards. The oceans were dark in some regions, chemically unstable in others, and often stratified into layers that varied sharply in temperature, salinity, and toxicity. The air above was still without oxygen, filled instead with volcanic gases and occasional ultraviolet bursts from a sun filtered only by haze. And yet microbes thrived. They did not need light in every case. They did not need oxygen. They needed energy, raw materials, and time, and the Archaean gave them those in abundance. The majority of microbial life at this time was prokaryotic, simple single-celled organisms without a nucleus. These were the earliest domains of life, bacteria and archaea. Both had adapted to survive in extreme environments. Some preferred heat, others preferred salt. Some thrived in acidic pools or near vents loaded with metals and sulfur. They were flexible, not in their forms but in their metabolisms, and that made them resilient. The murkiness of the Archean world wasn't just visual, it was chemical. The oceans were full of dissolved metals, especially iron, which in its reduced form remained soluble in anoxic water. Hydrogen sulfide, methane and ammonia were all present, varying by region. In this environment, microbes became specialists. Some oxidized sulfur, others reduced nitrates or sulfates. Some fed off hydrogen gas. These metabolic pathways became the scaffolding of the biosphere, invisible but essential. Microbes didn't float aimlessly. Many formed dense communities, clinging to mineral surfaces or growing as mats across submerged rocks and sediments. These mats were structurally simple, but biologically diverse. Layer upon layer of microorganisms created microenvironments, thin zones where gradients of light, temperature, or nutrients allowed different species to coexist. In the top layers, photosynthesizers captured energy from sunlight. Beneath them, anaerobic microbes fed on the waste products, creating a self-sustaining ecosystem without complexity and size. Some of these microbial mats left physical traces, stromatolites, but most did not. The majority of microbial life existed without ever leaving a direct imprint on stone. Its legacy is recorded instead in subtle chemical signatures, isotope ratios, mineral textures, organic carbon locked into sediments. These signals are faint, but they are consistent. They tell us that by the mid-Archean, microbial life was not just present, but widespread, adapted to a variety of environments, and capable of surviving major disruptions. Photosynthesis, even in its early forms, gave microbes an edge. Light was an abundant energy source, even filtered through a dusty atmosphere. Anoxygenic photosynthesizers used sulfur compounds or iron instead of water, producing sulfur or ferric iron rather than oxygen. These organisms could thrive in shallow water, particularly in environments near volcanic shores where chemical inputs were steady and light penetrated the surface. Their presence changed the local chemistry, affecting pH, redox balance, and the solubility of minerals. Oxygenic photosynthesis, the kind that splits water to release oxygen, emerged sometime during the Archean, most likely among cyanobacteria. This innovation did not create a breathable world overnight. For a long time, the oxygen they produced was absorbed by dissolved iron or organic matter, preventing it from accumulating in the atmosphere. But the process marked a turning point. It introduced a new chemical pathway with global implications. In the murky waters of the Archean Ocean, cyanobacteria began to alter their surroundings in more permanent ways. As they grew in colonies, their photosynthetic byproducts interacted with the water and the seafloor, forming oxides and precipitating minerals. They contributed to the formation of banded iron formations, thick layers of iron-rich rock that settled out of the ocean when oxygen bound with dissolved iron and rendered it insoluble. These bands, alternating between iron oxides and other sediment layers, are some of the most durable evidence for early biological activity. They show that microbial metabolism wasn't confined to isolated pockets. It was happening on a scale large enough to affect entire basins, repeatedly, over millions of years, and while they don't capture the microbes themselves, they record the consequences of microbial life, a biological process leaving behind geological artifacts. Elsewhere in the ocean, microbial communities adapted to different conditions. In deeper waters, chemosynthetic bacteria fed off hydrothermal vent chemistry, oxidizing hydrogen sulfide or methane, fixing carbon dioxide into organic matter without the need for sunlight. These communities likely formed the earliest analogues to ecosystems, complete with producers, recyclers, and waste processors, all operating on a chemical level. Archaea, distinct from bacteria but similarly structured, were well suited to extreme environments. Some lived in high-temperature regions, others tolerated salinity or acidity. They developed unique metabolic strategies, including methanogenesis, the production of methane from carbon dioxide and hydrogen. This process, still active in some environments today, contributed to the buildup of methane in the atmosphere, reinforcing the greenhouse effect and helping maintain Earth's surface temperature under a faint sun. The interplay between microbial life and the surrounding environment was constant. Microbes altered their chemical surroundings, which in turn influenced their own evolution. Minerals precipitated differently around microbial mats. Sediments accumulated faster or slower depending on microbial activity. In some regions, life became the dominant force shaping surface chemistry, even without being visible. Despite all this activity, there was still no oxygen in the air, no multicellular organisms, no food webs in the modern sense. Life was quiet, microscopic, and limited in its external impact. But it was laying the groundwork for what would come later. Every microbe that fixed carbon, oxidized sulfur, or produced methane was part of a larger system, a planetary engine turning energy into complexity. The murk of the Archaean wasn't just visual, it was conceptual. The boundaries between geology, chemistry, and biology were still blurred. Rocks hosted life. Life changed chemistry. Chemistry altered rocks. It was a world in which physical and biological processes were intertwined, difficult to separate and deeply dependent on one another. Over time, as microbial life continued to spread, its effects would become harder to ignore. Oxygen would begin to accumulate, first in shallow water, then in the atmosphere. Microbial communities would start to leave more permanent traces. The surface of the Earth would begin to reflect the presence of life, not just as a layer on top, but as a process within the crust, within the ocean, and eventually within the air. But even in this early phase, the dominance of microbes cannot be overstated. For billions of years, they were the only form of life on Earth. They filled every available niche, evolved rapidly, and shaped the chemistry of the planet in ways that still persist. Their legacy is not just historical, it is foundational, and as they grew, divided, and adapted in the Archaean murk, they brought the Earth closer to a transition, one that would not happen quickly, but one that would change everything. The quiet work of microbes layered over deep time would eventually shift the atmosphere itself, paving the way for a world with air that could be breathed, skies that could turn blue, and life that could finally grow beyond the scale of a single cell. In a world where almost nothing stayed still, stromatolites did. They grew where conditions allowed and remained where little else could. They didn't look like much. Not then, not now. Mounds, domes, sometimes flattened sheets. to the untrained eye just rock. But they were more than that. They were living architecture, built by the slow, repeating work of microbial communities laying down layer after layer of life and sediment, and they were everywhere the conditions were right. Stromatolites weren't the first life, but they were the first to leave a visible structural mark. Unlike the chemical traces left in isotopes or the microbial mats that decomposed without a trace, stromatolites persisted. They preserved the shape of the life that built them, and in doing so they preserved time. Not a moment, but a process. A repeated rhythm of growth and burial over years, centuries and millennia. The organisms responsible were mostly cyanobacteria, single-celled photosynthetic microbes capable of binding sediment grains and trapping them within thin, sticky layers. These bacteria lived in mats, packed together in thin films on shallow seafloors or along tidal flats. During the day, they captured sunlight and converted carbon dioxide into organic material. At night, they rested or processed the materials gathered in the light. Over time, as sediment settled on top of the mats, the bacteria migrated upward toward the light, rebuilding their position at the surface. New sediment would fall, the microbes would rise again. Each cycle added a new layer, thin but distinct, creating laminated structures that gradually rose from the seafloor like slow-growing domes. The layering wasn't just biological, it involved the interaction between life and environment. Sediment supply, water chemistry, currents, and microbial metabolism all played a part. The result was a structure both shaped by and resistant to its surroundings. Stromatolites could survive in places where other forms of life could not, in part because their mat-like communities protected each other. The outer layers shielded the interior from UV radiation, desiccation, and chemical changes. And as they grew, they altered the microenvironment around them. Some stromatolites formed in calm, shallow marine environments, where water depth varied only slightly and sunlight was abundant. Others grew in more turbulent settings, with waves and tides constantly disturbing the surface. The shapes of stromatolites varied with their conditions. Tall, columnar forms in deeper water, flatter, more encrusting types in places with stronger currents or sedimentation. They were not isolated phenomena. Archaean stromatolites appear in many locations around the world, in Australia, South Africa, Canada and beyond. Their global distribution suggests that wherever conditions allowed, these structures emerged independently. They weren't confined to a single habitat or event. They were a strategy, a way for life to persist and protect itself, and that strategy worked across vast distances and timescales. And while the forms of stromatolites are simple, their presence marks a shift. Before stromatolites, life was mostly invisible. After them, it had physical impact. The seafloor was no longer just shaped by currents, tides, and sediments. It was also shaped by biology. Microbial life was not just reacting to its surroundings, it was building. In doing so, it began to change the world around it. Photosynthesis, especially by cyanobacteria, produced oxygen. At first, this oxygen reacted with dissolved iron in the oceans, forming insoluble iron oxides that settled out of solution and created banded iron formations. But over time, as these sinks filled up, more oxygen remained in the water and eventually began to escape into the atmosphere. Stromatolites played a central role in this slow transformation. As visible hubs of microbial photosynthesis, they contributed to the global oxygen budget. Not in a dramatic, explosive way. This wasn't a revolution, it was a long, steady climb. But the oxygen they released began to accumulate. At first locally, in the shallow marine waters around the structures, then more broadly, as photosynthesis became more widespread and the balance of gases began to shift. This shift wasn't smooth. Oxygen is reactive, and it triggered changes in ocean chemistry that sometimes destabilized ecosystems. Some anaerobic organisms adapted to life without oxygen, were pushed to more marginal environments. Others adapted, evolved new pathways, or died off. Oxygen created both opportunity and disruption, forcing life to change or move. But the stromatolites remained. For much of the Archaean, they were dominant forms of life in the visible landscape, not just living in it, but shaping it. They altered water flow, trapped nutrients, and created small-scale ecosystems within and around their structures. They were habitat and organism in one, environment and inhabitant combined. They also began to change the sedimentary record. The laminated textures of stromatolites were different from purely physical sediment layers. Their presence marked environments where biology had influenced deposition. Their geometry preserved wave action, tide cycles, and seasonal changes in light and nutrient availability. Reading stromatolites is like reading a diary written in stone. Slow, repetitive, but rich in implication. Even their decay contributed to future life. As stromatolite mats died, they released organic matter into the surrounding sediment. This material became food for other microbes, helped bind sediments, or participated in chemical reactions that shaped the mineralogy of the seafloor. In this way, even death in the stromatolite world became part of the construction process. Today, modern stromatolites are rare, but not gone. They exist in isolated hypersaline environments, places too extreme for most grazing organisms that would otherwise destroy the mats. But in the Archaean, there were no grazers, no animals to disrupt the surface, no predators to consume the mats. Microbes were free to build uninterrupted, and they did. This period, when stromatolites were widespread, represents one of the earliest examples of ecosystem engineering, life altering its environment in a sustained and large-scale way. The structures didn't rise fast. They didn't spread quickly, but they endured. And over time, they laid the groundwork for future complexity. They altered the chemistry of the ocean. They influenced atmospheric composition. They created conditions in which other organisms, perhaps not yet imagined, could eventually thrive. And they told a story, not through language, but through form. A dome on the seafloor, a ripple in the sediment, a trace of structure where none had existed before. These weren't fossils of bodies. They were fossils of behaviour, the record of repeated, persistent action, of life adapting and organising and building over time. As Earth moved slowly toward a more oxygenated future, stromatolites were already part of the transition. They had no plan, no foresight, but their activity created the conditions in which more dramatic changes could eventually unfold. The stage was still small, the actors still microscopic, but the script was starting to shift. The biosphere, once hidden, was beginning to leave its mark not just in chemistry, but in shape. And as the planet changed in response, it opened the door for new forms of interaction between life and rock, life and light, life and the very air itself. What came next wouldn't be immediate, but the trajectory was set. Life had found a way to build, and eventually it would learn to build even more. The oceans had life, the surface had sunlight, the atmosphere had weather, but what it didn't have, not yet, was breath. At least not the kind that moves air into lungs, draws oxygen into blood, and fuels muscle and motion. Breathing in that sense wasn't even on the table. The world simply hadn't made the air for it yet. There was no shortage of gases in the Archaean atmosphere. It was thick with carbon dioxide, heavy with water vapour, laced with methane and ammonia and sulphur compounds. But oxygen, the molecule that defines modern respiration, metabolism and consciousness, was barely present. Microbes had started to produce it through photosynthesis, yes. But the Earth wasn't letting it go free, not yet. Every atom of oxygen released into the ocean was immediately seized by something else, most often iron. The oceans were saturated with ferrous iron, dissolved and waiting. When oxygen encountered it, the reaction was fast and complete. Ferrous iron became ferric, precipitated out of solution and settled to the bottom as rust-red minerals. The oxygen didn't linger, it didn't accumulate, it got used. Even once the iron was tied up and settled into the rock record as banded iron formations, other sinks remained. Volcanic gases absorbed free oxygen. Organic matter soaked it up during decay. Sulfur compounds were oxidized. The chemistry of the early Earth was built around oxygen's reactivity, and for a long time that meant it was rarely allowed to stick around. So for billions of years, life got by without it. Anaerobic metabolisms, those that don't require oxygen, dominated. Microbes used fermentation, or relied on chemical reactions involving sulfur, nitrogen, or hydrogen. Some used light, but not to split water or make oxygen. Others fed on molecules leaking from the seafloor or released by volcanic eruptions. The range of metabolic strategies was wide, and most of them didn't just work without oxygen. They depended on its absence. Respiration, as we know it, hadn't evolved because it couldn't. You don't build a complex oxygen handling system in a world that offers none. And without oxygen in the environment, there was no evolutionary incentive to extract energy from it. Other pathways worked well enough, especially for single-celled organisms. There was no pressure to do more. But that was beginning to change, slowly. Microbes like cyanobacteria were releasing oxygen into their local environment, and some of that oxygen stuck around, in micropockets, within microbial mats, or in water layers near the surface. These regions became oases of oxidation, chemically distinct from the anoxic world around them. They were small, but they were persistent. In these microenvironments, new pressures emerged. Oxygen could be toxic to organisms that weren't prepared for it. It damaged proteins, disrupted membranes, and altered metabolic reactions. Microbes that had evolved in its absence suddenly had to find ways to cope. Some avoided it. Others evolved defenses. A few found ways to use it. The step from oxygen tolerance to oxygen use was gradual. But once it began, the payoff was enormous. Aerobic respiration, the process of extracting energy from organic molecules using oxygen, is far more efficient than anaerobic pathways. It yields more energy per molecule of food, allowing organisms to grow faster, move more, or build more complex structures. But in the Archaean, that potential was still mostly unrealized. The environment wasn't ready, the oxygen wasn't available in high enough concentrations, the chemistry hadn't caught up to the possibilities. Even so, traces of adaptation were beginning to appear. Some microbes developed enzymes to neutralize reactive oxygen species, byproducts of accidental oxygen exposure. These protective systems, over time, could evolve into tools for using oxygen intentionally. But the leap wasn't forced, it wasn't urgent. Oxygen was still scarce. Anaerobic life still ruled. The air itself reflected that reality. It didn't support combustion, it couldn't sustain flame. There were no fires, no oxidative weathering, no rust on land. Rocks exposed at the surface were altered by water, not by air. Soils didn't form the way they do today. There were no forests, of course, no lungs breathing in and out. But more than that, there was no air to support breathing in the first place. The absence of oxygen meant the absence of a whole category of processes. No aerobic decomposition, no large-scale ozone layer, no visible signs of respiration. The Earth was active, alive, but quiet in a way that's hard to imagine now. No wind whistling through leaves, no chirping, no breathing, no sound shaped by air and throat and muscle. Just chemical cycling, microbial mats, and a sky-tinted pink or orange, depending on the methane. We tend to think of breathing as a basic function, something elemental to life. But on the scale of Earth's history, it's a late arrival, an adaptation to a changed world, not a starting point. For most of Earth's existence, respiration was microbial, slow and anaerobic. Breathing wasn't missing, it simply wasn't needed. And yet, the seeds were there. The microbes photosynthesizing in the shallow seas, the mats building stromatolites, the the occasional oxidative burst in small pockets of water, all of it was preparation. Quiet, cumulative, and eventually irreversible. The sinks that absorbed oxygen were slowly filling up, the sources that produced it were growing, and the balance was starting to shift. No one would have noticed. There were no lungs to inhale the change, no minds to perceive it. But the chemistry was moving. The Earth was heading towards something unfamiliar, not because of an event, but because of a threshold. One that once crossed could not be undone. Breathing wasn't invented yet, but the world was beginning to build the conditions that would one day make it possible. Oxygen was no longer just a byproduct. It was becoming a force, and eventually it would tip the scales, changing the air, changing the ocean, and changing what life could become. If you had somehow found a way to stand on solid ground during the Archean, beneath a dimmer sun and above greenish seas, you wouldn't have stayed there long. The air would kill you, the radiation would strip your skin, and the heat, in many places, would be unbearable. But even if you could ignore all that, somehow stand there safely, there would be something else that felt strange without you quite being able to name it. The day would pass too fast. Because the Earth spun faster then. A full rotation took only about 14 hours. The reason has nothing to do with the atmosphere or the crust or anything on the surface. It's a matter of physics, baked into how the Earth formed and how it's changed since. After the planet's violent beginning, and especially after the giant impact that formed the Moon, the Earth was left spinning rapidly. That momentum persisted. Over billions of years it's been slowing down, but only gradually. The mechanism behind that slowdown is the Moon itself. The gravitational interaction between Earth and Moon causes tidal friction, a subtle but constant drag as the ocean bulges try to align with the Moon's pull, but lags slightly behind due to Earth's rotation. That drag transfers angular momentum from the Earth to the Moon, pushing the Moon slightly farther away while slowing Earth's spin. The result? Longer days. But during the Archean, this process was still in its early stages. The Moon was much closer, perhaps only about 200,000 kilometres away, less than 2/3 its current distance, and the tides it caused were more extreme. Ocean bulges were larger, coastal zones experienced stronger, more dramatic shifts in water level, and the Earth itself rotated quickly, completing a full spin in under 2/3 the time it does today. This shorter day had consequences, not just in terms of sunlight hours, but in how energy cycled through the environment. Faster rotation meant stronger Coriolis effects, which influence wind and ocean currents. It meant shorter exposure times to the sun for any given location, which could impact surface heating patterns and, indirectly, climate dynamics. And for early life, especially photosynthetic microbes, it meant that light and dark cycles were fundamentally different than what they are now. The microbial mats growing in shallow seas had to adapt to this rhythm. Daylight hours came and went quickly. The window for photosynthesis was narrower. Night came sooner. That shift affected metabolic cycles, growth rates, and the structure of microbial communities. Some organisms may have evolved to maximize energy capture in short bursts. Others might have leaned on internal rhythms, primitive circadian mechanisms, to anticipate light and dark and prepare accordingly. It's unclear exactly how tightly early microbes were tied to the day-night cycle, but it's reasonable to think the rhythm mattered. Photosynthesis, for example, is sensitive to light availability. Growth rates change depending on the balance of energy production and storage. A 14-hour day would affect how organisms manage those processes, especially in environments where competition was tight and resources were thin. The shorter day also meant more days per year. The Earth's orbital period, the time it takes to go around the Sun, hasn't changed significantly. But with shorter rotations, there were more rotations within a single orbit. That means more sunrises, more sunsets, and more tidal cycles in a given year. The frequency of tides, in particular, would have been striking. Some coastlines might have seen multiple significant tides per day, each stronger than those we see now due to the moon's proximity. That tidal energy had geological effects as well. It stirred shallow seas, drove sediment redistribution, and shaped coastal microenvironments. In these zones, where water levels rose and fell dramatically and regularly, microbial mats would have found both opportunity and challenge. Tides could expose mats to air briefly, triggering chemical changes. They could also erode and reshape habitats, forcing communities to rebuild. But that disruption also moved nutrients, oxygenated shallow water layers, and opened new surfaces for colonization. The stronger tides and faster planetary spin may also have contributed to stronger ocean mixing. In an Archean world where the surface ocean was chemically different from the deep, vertical mixing mattered. It helped cycle nutrients. It allowed oxygen from photosynthesis to penetrate slightly deeper. It distributed iron, sulfur, and other compounds in ways that affected microbial metabolism. A fast-rotating Earth wasn't just spinning quickly. It was churning itself, subtly but constantly. For the planet as a whole, faster rotation meant more intense weather systems. Wind patterns were shaped differently. Storms, if they existed in recognizable forms, would have behaved in unfamiliar ways. Atmospheric circulation, though still primitive in its modern structure, responded to the Coriolis effect, which intensifies with shorter days. That means cells of rising and falling air, the large-scale conveyor belts of planetary climate, may have been narrower and faster. Even the shape of Earth itself was slightly different. Faster spin created more centrifugal force, which caused the planet to bulge more at the equator. That equatorial bulge would affect ocean depth distribution, gravitational pull, and even how water moved across the surface. None of these differences were enormous on a human scale, but they added up across billions of years. They shaped how continents formed, how seas behaved, and how life adapted. And all of this was happening silently, in a world without clocks or calendars. Time moved at its own pace, set by physics, slowed gradually by the moon. Life adjusted. It had no choice. The rhythms of Earth were not optional. They were the background conditions that shaped what could evolve and how it would survive. The most striking part of this isn't that days were short. It's that they've been lengthening ever since. Every century, the Earth's rotation slows by a fraction of a second. The moon continues to drift away, a few centimetres per year, and the tides pull at the planet like a slow break. It's barely noticeable, but over billions of years it changes the structure of experience itself. What we call a day is not fixed, it's a moving target. In the Archaean, no one was watching the sky and measuring the hours, but time was still passing, and the way it passed quickly with more cycles per orbit, more tides per day, and more sunrises per year, left its imprint. Not in clocks, but in sediments, in ripple marks on ancient shores, in layered stromatolites responding to light, in the wear patterns of rock shaped by water that rose and fell in regular, tireless rhythm. The Earth was rotating fast, moving forward, dragging everything along with it, microbes, minerals, oceans, and atmosphere. And all of it was bound together by motion, not just in space, but in time. A time that was not yet counted in 24-hour days, a time that spun by faster, but still slow enough to shape a world. The early Earth didn't have a lot going for it, at least in terms of protection. No ozone layer, no thick forests to filter sunlight, no atmosphere safe to breathe. But beneath all that, below the crust, beyond the surface chaos, something was working in its favour. Something silent, planetary and persistent. A magnetic field. This field didn't announce itself, you couldn't see it, you couldn't hear it. But it was there, extending far out into space in invisible arcs, deflecting charged particles from the sun and the wider galaxy. These particles, solar wind, cosmic rays, high-energy radiation, bombard planets indiscriminately. They strip away atmospheres, shred molecules, and turn surfaces into wastelands. But Earth had a shield. The magnetic field came from the core. Deep inside the planet, the inner core was likely already solidifying, or at least beginning to. Around it, the outer core was molten, a layer of liquid iron and nickel swirling under pressure, moving in vast convective patterns. As this conductive fluid moved, it generated electrical currents. Those currents in turn produced a magnetic field. The process is known as the geodynamo. It's a system that maintains itself. Motion creates current. Current creates field. Field influences motion. And the result is a planetary magnetic bubble, stretching tens of thousands of kilometers into space. This field doesn't stop solar wind completely, but it diverts most of it, guiding particles around the planet, trapping some in radiation belts, and preventing the constant erosion of Earth's atmosphere. Other planets, like Mars, weren't so lucky. Mars may once have had a magnetic field, but it faded early. Without that protection, solar wind gradually stripped away its atmosphere. Over time, what remained was thin, cold, and incapable of supporting surface water. Earth, by contrast, held on, not just because it was in the right spot, but because it kept its core active. In the Archaean, this protection was critical. The sun was more active then, younger, more volatile, producing frequent solar flares and bursts of charged radiation. Earth's atmosphere, still developing, had little capacity to block high-energy particles on its own. Without a magnetic field, much of the water and air might have been lost to space, pulled upward, and flung away by the constant assault of solar wind. The field also helped preserve the chemical stability of the upper atmosphere. It reduced the stripping of hydrogen, which otherwise might have escaped into space over time, and helped maintain the conditions necessary for surface water to persist. It didn't make the Archean Earth safe, but it made it survivable. Life, still microscopic and confined mostly to oceans, may not have needed to understand any of this, but it benefited from it constantly. UV radiation from the sun was still a problem. There was no ozone layer to absorb it, but the most dangerous cosmic particles were largely deflected or absorbed before they reached the lower atmosphere or surface. That reduction in radiation allowed more stable environments to develop, especially in water. Magnetic fields leave few obvious traces in the fossil record, but they do leave clues in rocks. Certain minerals, especially iron-bearing ones, align themselves with the magnetic field during formation. When lava cools or sediments settle, these mineral grains lock into place, preserving the direction and strength of the field at that time. Studying these alignments, known as paleomagnetism, allows scientists to track the history of Earth's magnetism. From Archean rocks, we know the field existed. It was weaker than today's, possibly more chaotic, but it was present, and it was strong enough to deflect solar particles and help retain the atmosphere. This invisible system, born from deep Earth processes, was a quiet partner in the survival of early life. It also played a role in navigation, not for animals, not yet, but for charged particles and electric currents in the upper atmosphere. It influenced how auroras formed, where radiation was deposited, and how the ionosphere behaved. These effects are subtle but widespread. They shape atmospheric chemistry. They affect the distribution of energy in the planet's upper layers, and in a time before biology had teeth, eyes, or lungs, they were part of the operating conditions life had to work with. Some hypotheses suggest that hydrothermal vents, possible cradles of life, might be influenced by local magnetic variations, either through rock magnetism or electrical conductivity in the surrounding environment. It's speculative, but it underscores the idea that magnetism wasn't just a planetary defense. It may have shaped habitability in ways we still don't fully understand. Over time, the magnetic field would fluctuate. It would reverse polarity, strengthen and weaken, shift its configuration. But it never stopped. As long as the core stayed active, the shield remained. And as Earth's surface changed, As continents formed, oceans evolved, and life became more complex, the magnetic field stayed in place, always silent, always working. Today, we depend on it without thinking. It protects satellites, it guides migratory animals, it defines space weather, and it still guards our atmosphere from solar stripping. But its roots go all the way back, to a time when Earth's interior was hotter, its crust thinner, and its surface chemistry raw. In that world, life had almost no defences, except this one, a planetary field generated from below, reaching out into space and holding back the worst of what the universe had to offer. Even now, we don't fully know how long the field has persisted without pause, or how exactly it began. But its presence in the Archean is clear. It was there when the air couldn't be breathed, when the sky was pink and the water was green, when microbes layered themselves into domes of sediment to reach the sun. It shielded without fanfare, and that was enough. While oxygen was still being figured out, while continents were still thinking about forming, and while days passed in short, spinning cycles, the magnetic field was already active, not seen, not understood, but essential. The Earth was protecting its own surface before anything on the surface even knew what danger was, and with that protection, life had the chance to keep going, to explore, to evolve, to wait patiently for the world to change. It's almost impossible to imagine Earth without life, not because we can't picture it visually, but because we can't imagine the silence. Not the kind you find in a quiet forest or a still morning, but something deeper, a kind of silence that has never heard wind through leaves, or the rustle of grass, or the chirp of a single living thing. During the Archaean, the land was lifeless in every visible way. There were no plants, no insects, no animals. No roots held the soil, no leaves caught the light. The idea of a tree hadn't been invented yet. Even the concept of soil is misleading. What little material covered the solid ground was not soil in any modern sense. It was loose rock, fragmented by weather or volcanic activity, occasionally shaped by tides or chemical interactions, but never by biology. Without plants, there were no forests, no undergrowth, no meadows. Without moss or fungi or lichens, all of which would come much, much later. There were no pioneer species clinging to rock and beginning the slow work of organic transformation. The continents, or the few large land masses that existed, were bare. Their surfaces were jagged, sharp, unstable. Volcanic flows, basaltic plains, and slowly forming proto-cratons dominated the terrain. Erosion happened, but without roots to anchor loose material, it was often extreme. Rain fell and carved channels, wind lifted particles and carried them away, but there was no ecosystem to moderate the violence of the elements, and that brings us to the absence of sound. In a world without birds, mammals, amphibians, or even insects, the land would have been overwhelmingly quiet. No buzzing, no howling, no chorus of night or song of morning. The only consistent sound would have been wind, though even that would have sounded strange. Without trees or vegetation to catch it, wind moved across bare rock and open ocean. It didn't whistle through leaves. It scraped and echoed, maybe howled through volcanic ridges or rushed across barren slopes, but it carried no life. The crash of waves existed, though the coastline was shaped differently. Tides, especially with the moon much closer, were more intense. Water struck rock more forcefully, and over time those impacts shaped shores and basins. But the waves did not pull seaweed. They did not toss shells. There were no sandy beaches filled with burrowing creatures, no tidal pools with crabs or anemones, just water and rock grinding against each other in a cycle that had no audience. Occasionally volcanic activity would break the monotony. Explosions, rumbles, gas releases, ash could cloud the sky. Lava could pour into the ocean, boiling it, sending up plumes of steam. But even these events were followed by silence. No animals fled. No predators took advantage of the disruption. The land simply endured. Even underground, there was no activity in the way we understand it now. No worms aerating soil, no insects burrowing or decomposing organic matter. The Earth's crust moved, flexed, cracked, but it did so alone. Life had not yet learned how to live on land. All of biology was still confined to water, and only in some parts of it. The colours of the landscape reflected this. No green, obviously. Mostly greys, blacks, browns, the colours of rock and ash. Maybe the occasional chemical staining from minerals, reddish iron oxides, yellow sulphur deposits, pale crusts from evaporated salts. But nothing like the saturated palette of modern Earth. No seasonal change, no spring bloom, no fall decay. The land didn't change because nothing was living on it to change with the seasons. Sunlight hit the surface without resistance. No canopy filtered it. No shade protected the ground. On days when the sky was clear, UV radiation reached all the way to the rocks. On days when volcanic haze or methane-induced smog filled the air, the light dimmed and reddened, but even then nothing stirred in response. The Earth turned under the sun, untouched. And yet, life knew this land existed. Microbes didn't live on it, not yet, but they felt its presence. Rivers carried nutrients down from these rocky slopes. Erosion added minerals to shallow seas. Volcanic activity poured elements into the water that microbes used for metabolism. The land and the ocean weren't separate. They were in conversation, even if one side was still silent. Eventually that silence would end. Microbes would begin to colonize damp surfaces near the waterline. Over long time scales, they would adapt to desiccation, to radiation, to low nutrient environments. They would begin to form crusts, microbial layers that could trap dust, fix nitrogen, and survive in harsh conditions. But in the Archean, those experiments were still ahead. The land remained quiet, and still, for all its emptiness, the land was essential. It was the place where continental crust was forming, thick, buoyant blocks that resisted subduction. It was where weathering began to draw carbon dioxide out of the atmosphere, slowly shaping the planet's climate. It was where the record of Earth's deep history would be written in layers of volcanic rock, sediments, and minerals altered by water. Even in its silence, it was storing information. Today, it's hard to find a landscape untouched by biology. Even deserts hum with microbial activity. Even the harshest cliffs host moss or lichen. But the Archean land was untouched in the truest sense. Not pristine, but unclaimed. It had not yet been used as habitat, not yet converted by roots or reshaped by animals. It was raw. The silence of that land was not peaceful. It wasn't the quiet of stillness after motion. It was the quiet of absence. Not of noise, but of participation. Nothing breathed there. Nothing died there. Nothing tried to hold on or take shelter. It was Earth, not yet a home, but waiting. And from the perspective of life in the ocean, the land must have seemed distant, irrelevant, maybe even dangerous. But it was part of the same system. The same tides that shaped coastlines fed nutrients into the sea. The same volcanoes that built islands altered ocean chemistry. The land was part of the loop, even if no one was there to walk across it or listen to its silence. One day that would change. Life would begin to climb out, to touch rock, to survive sunlight, to breathe air. But for now, the land stood still, unburdened by life, unbroken by roots, and above it, a sky with no birds. Below it, a world building slowly towards something more. The Archean Earth was hot, but not in the way we usually understand it. It wasn't dotted with flames, and it didn't blaze with open fire, because fire in the conventional sense didn't really exist yet. Fire, as we know it, needs oxygen. Combustion is a reaction. Fuel meets air and heat does the rest. But the Archean had no air to burn. Oxygen hadn't accumulated. The materials were there. Carbon-based matter, volcanic gases, heat everywhere. but the spark couldn't catch. Not until the chemistry of the planet changed. So instead of flames, the heat came from below, from the planet's interior, still bleeding off the energy of its violent formation. Heat from radioactive decay, from residual energy trapped in the core, from constant tectonic motion. That heat moved upward, through the mantle, reaching the surface in eruptions and flows, in steaming fissures and molten plains. Lava poured, not with sudden bursts like modern volcanoes, but sometimes in sheets. Slow, wide basaltic flows that covered landscapes and built new ground. There were places on the Archean Earth where rock barely had time to solidify before being buried again in another layer of lava. The crust was thinner then, more flexible, more prone to cracking. Heat moved through it more directly. Volcanic islands emerged and vanished. Ocean ridges split open and oozed molten rock into the sea. Even areas not actively erupting were hot beneath the surface. Geothermal gradients were steeper. The land, if you could call it that, often steamed without a flame. This constant geothermal activity made the Earth feel alive in a mechanical way. Not organic, but dynamic. Heat changed water chemistry. It built hydrothermal systems that powered microbial metabolism. It fractured rock and fed minerals into the sea. It created pockets where life could hide from UV radiation and find nutrients in chemical gradients. Life, such as it was, didn't just survive heat, it needed it. But heat wasn't everywhere, and its absence didn't mean calm. Just as fire couldn't exist without oxygen, ice couldn't form easily either. Not in the same dramatic glacial ways we see now. There's debate over just how cold the Archean Earth got. Some models suggest the planet remained warm, thanks to greenhouse gases like methane and carbon dioxide, which trapped heat from the dimmer young sun. Others propose that temporary cooling events did occur, that clouds of volcanic ash or shifts in carbon cycling may have led to brief cold periods, maybe even early glaciation in isolated regions. But even if ice formed, it did so without the usual visual cues. There were no snowy mountaintops, no polar caps stretching across continents, no ice sheets grinding valleys into the crust. The land was too raw, the atmosphere too thin, the ocean chemistry too different. If ice came, it came quietly. It didn't reshape the world the way glaciers eventually would in later eons. The cold, when it happened, didn't need snow to be dangerous. A dip in temperature could alter ocean circulation, affect the solubility of gases, change the chemistry of shallow basins where microbial life was most active. Cold could slow photosynthesis. It could make nutrient cycling less efficient. Even small shifts had big consequences, not because life was fragile, but because it was simple. With few backups and no complex ecosystems, a failed microbe community might mean nothing recolonized the area for centuries. Still, the dominant climate leaned warm. The sun, in its early days, gave off less light than it does now, roughly 70 to 75% of today's output. By all accounts, that should have left the Earth frozen, but it didn't. Greenhouse gases made up the difference. Methane in particular was abundant, produced by early microbes and volcanic activity alike. Methane traps heat efficiently, more so than carbon dioxide, and in the absence of oxygen, it could build up to levels that would be toxic today. This greenhouse effect kept the oceans liquid, the atmosphere active, and the surface temperate enough for water to flow, not freeze. But the balance was delicate. Too many volcanic eruptions, too much weathering, or even biological shifts could tip the scales. Earth's temperature wasn't locked in, it drifted. Not seasonally, not even on human timescales, but on geological ones. Millions of years up, millions of years down. Local conditions varied wildly. Shallow seas warmed by sunlight and geothermal activity could be near boiling in places. Deeper waters, cut off from circulation, might be cold, dense, and stagnant. Hydrothermal vents created isolated environments with temperatures ranging from freezing just a few meters away to hundreds of degrees near the vent mouth, and on land, bare rock baked under a hazy sun during the day and radiated its heat away quickly at night, with nothing, no vegetation, no insulating soil, to moderate the swing. There were no forests to hold moisture, no clouds shaped by transpiration, no living ground cover to soften the extremes. Rain, when it fell, hit bare stone or volcanic ash. It pooled in uneven basins. It carved gullies and ran off quickly unimpeded. Water evaporated fast in some areas, froze in thin crusts in others, and the atmosphere, with its mix of methane, CO2 and other gases, carried heat unevenly. Some areas scorched, others cooled too fast. There was no global thermostat, no planetary comfort zone, and yet life endured. Because these extremes, this heat without fire, this cold without ice, were not chaos. They were the environmental conditions life was born into. Microbes didn't expect comfort. They didn't wait for stability. They used what was there. They built communities around hydrothermal systems, adapted to UV exposure, evolved metabolisms suited to high temperatures or chemical gradients that only existed in narrow ranges. To us, the Archaean might look uninhabitable. No green, no blue sky, no oxygen, and no comforting warmth. But to the life that evolved in it, it was all there was. Heat came from within the earth, not from combustion. Cold came from a dim sun and a still-forming atmosphere, not from snow. The extremes weren't extremes to them. They were normal. And within those conditions, Earth's long experiment continued. With every lava flow, every volcanic winter, every fluctuation in methane or solar output, life adjusted. Not dramatically, not quickly, but with time. Because while Earth didn't yet have fire or frost, it had energy, it had water, and it had the potential, not just for change, but for persistence. In that sense, the Archean climate wasn't hostile, it was formative. It shaped what life could become by limiting what it could do. And as the crust cooled, as the days lengthened, as the chemistry of air and ocean began to drift towards something more familiar, that early life was ready to follow, moulded not by comfort but by extremes. The moon didn't hang quietly in the Archaean sky the way it does today. It wasn't a distant companion casting gentle light across calm oceans. It was nearer, much nearer, nearly twice as large in the sky, and more than twice as powerful in its gravitational influence. It was still moving away, bit by bit, but during the Archaean, it was close enough to stir the seas like a giant spoon. And it mattered. The moon had already been around for a while by the time the Archaean began. Its origin was violent. A planetary collision with a Mars-sized body named Theia, an impact that tore apart Earth's early crust and threw molten debris into orbit. That debris coalesced into the moon, and the Earth-Moon system settled into a shared gravitational rhythm. But it was a rhythm that began with chaos. Energy had to dissipate, orbits had to stabilize, and the effects lingered. In those early days, the moon was not just a visual feature, it was a force. Its gravity pulled at the Earth, deforming the planet's crust, creating tides not just in water but in rock. The tidal bulges shifted slowly across the surface as Earth rotated, creating friction, and that friction mattered. It converted kinetic energy into heat. It slowed Earth's spin. It pushed the moon outward. The same dance continues today, but back then everything moved faster and hit harder. Because the moon was closer, its tidal pull was stronger. Estimates suggest the Archean ocean tides may have been 10 times greater than they are now. That means coastlines changed dramatically, multiple times a day. Water surged inland, retreated quickly, exposed microbial mats, then drowned them again. These shifts weren't subtle. They were sculpting tools. They carved shorelines. They distributed sediment. They created zones of chemical mixing that allowed nutrients to concentrate in places shallow enough for photosynthetic microbes to use them. For early life, this mattered more than sunlight alone. The tides created predictability in a world with very little of it. They regulated access to light and nutrients. They exposed surfaces to the air, such as it was, and then submerged them again in seawater. This rhythmic disturbance became a kind of clock, a schedule, and life, still microscopic, still struggling to establish itself, responded. Mats grew in patterns that matched the tides. Colonies adapted to survive brief exposure. Chemical reactions accelerated during transitions between wet and dry. Without the moon, that rhythm wouldn't have existed. The sun creates tides too, but they are weaker, and their influence doesn't produce the same high-frequency shifts. The moon's gravity made the Archean world dynamic in a way that static chemistry could never match. It stirred, it pulled, it drove circulation in shallow basins and may have influenced early ocean mixing on a global scale, and it shaped the length of the day. As Earth's rotation slowed due to tidal friction, the day lengthened, from a frenetic 6 hours after the moon's formation to about 14 hours during the Archaean to the 24 we live with now. This change was gradual but relentless. It altered everything from wind patterns to energy distribution, and again, it was the moon doing the work. The moon's position in the sky was not constant. It rose and set, shifted through its phases, but because it was so much closer, it would have appeared enormous, filling a large portion of the horizon, glowing not with firelight but with the cold reflection of a young sun. There were no eyes to see it, no organisms on land to watch it rise, but it was there, every day and night, tugging invisibly at water, stone, and time itself. We don't know exactly how much of the moon's surface was geologically active during the Archean, but its impact on Earth was clear. The tides helped stabilise the planet's tilt, a major factor in long-term climate stability. Without the moon, Earth's axial tilt could wobble dramatically over millions of years, swinging from near zero to chaotic extremes. With the moon, the tilt stays within a narrow range, keeping seasons relatively predictable and helping maintain temperature gradients that support ocean circulation. And while the moon doesn't produce light of its own, its phases would have created a secondary rhythm in the Archean world, a slow pulse of bright and dim nights, full moons and new moons, reflected across the oceans. For microbial life in the sea surface, this periodic change in light might have been detectable. For life in tidal zones, the alignment of lunar and solar tides created especially extreme shifts, spring tides that reached farther inland or withdrew more dramatically. Eventually the moon would become a reference point, a timekeeper, a symbol, an anchor for calendars and stories. But in the Archean, it had no mythology. It was just gravity, just motion. And yet, its influence was profound. It helped regulate the Earth's rotation, stabilize its climate, drive its ocean dynamics, and give early life something close to a rhythm. Today, we rarely think about that influence. The tides seem passive, the moon feels distant, but it is still moving away, about 3.8 centimeters per year, and Earth is still slowing down. In time, days will lengthen further, the moon will orbit farther, and yet its ancient role remains etched in rock, in banded sediments shaped by tidal currents, in the fossils of stromatolites that grew in tune with the sea, in the chemical layers that record wet and dry cycles across billions of years. Back in the Archean, the moon wasn't just in the sky. It was in the water, in the rock, in the spin of the planet itself. It didn't speak, but it moved, and the Earth, from its crust to its tides to the earliest living cells drifting in shallow seas, answered. It was there, leaking out in small amounts, long before it could do anything noticeable. Oxygen, made by microbes quietly harvesting sunlight, splitting water, and discarding a waste product that no one yet needed. In the early oceans, cyanobacteria had already figured it out. Oxygenic photosynthesis, a way to use water and carbon dioxide to build sugars and release energy, and with it, they released oxygen into the world. but the world had no place for it yet. The story of oxygen on Earth is not one of immediate transformation. It's a story of waiting, of slow accumulation, of resistance, of everything in the environment trying its best to neutralize, absorb, and bury oxygen before it could build up. And for a long time, hundreds of millions of years, the environment succeeded. In the Archean oceans, oxygen was instantly consumed by iron. Dissolved iron, abundant in the anoxic seawater, reacted with the free oxygen, forming insoluble ferric compounds that sank and collected on the seafloor. This reaction built the layered rock structures we now call banded iron formations, deep red and grey stripes that mark ancient episodes of oxygen release and removal. These formations appear across the Archean timeline, quiet evidence of a planet absorbing as much oxygen as it could, as fast as it could. The oxygen produced by photosynthesizers also reacted with sulfides, methane, and other reduced compounds in the ocean and atmosphere. These reactions stripped oxygen out of circulation. They stopped it from accumulating in the air. The oceans were the first battleground, a chemical war between production and removal, and life itself was generating both sides of the fight. Cyanobacteria created oxygen. Other microbes consumed it or created compounds that neutralized it. The balance was always in motion, always delicate. It wasn't just a matter of quantity, it was about thresholds. Oxygen had to reach a certain level before it could begin to persist, before the sinks became saturated and the surplus started to linger. Until then, every oxygen molecule was essentially erased. And yet, the microbes kept making it. Not for us, not for the future, just because it worked. Oxygen was a byproduct, not a goal. For the microbes performing photosynthesis, it was the waste they had to release to keep growing, and that growth was driven by energy. Light came in from above, filtered through haze and cloud, and in the right places, shallow seas, tidal flats, protected lagoons, it was enough. Microbial mats layered themselves across surfaces. They photosynthesized during the day, they processed nutrients at night, they built domes, they spread. And all the while they kept leaking oxygen into a world that wasn't ready for it. Some of that oxygen stuck around in microenvironments, tiny zones within mats where chemistry had shifted, thin surface layers of water where light penetrated and oxygen hovered just long enough to matter. These were islands of habitability in an otherwise hostile sea, and in those islands biology started to adapt. Some organisms developed ways to detoxify oxygen, others began to exploit it, but they were still outliers living in bubbles of chemistry surrounded by a vast anoxic world. Meanwhile, oxygen's slow, quiet assault on the planet continued. It changed mineral structures. It altered weathering rates on land. It affected the solubility of metals in the ocean. Each small change fed back into the system. Some changes encouraged more oxygen production. Others limited it. The whole planet was involved, not passively but chemically, in resisting and eventually enabling the rise of this reactive gas. The long wait for oxygen is sometimes called the oxygen lag, the period between the evolution of oxygenic photosynthesis and the moment when oxygen began to accumulate in the atmosphere. That lag lasted for more than 1 billion years. For perspective, that's longer than all multicellular life has existed. It's longer than the time since the first animals appeared. It's an immense stretch of geological patience, and during that time, life was still experimenting, still spreading, still inventing new ways to survive. The absence of oxygen didn't stop evolution, it just shaped its direction. Anaerobic metabolisms remained dominant. Chemosynthetic communities near hydrothermal vents flourished. Microbes used sulfur, nitrogen, hydrogen, anything but oxygen, to power their survival. In some cases, the appearance of oxygen created stress. It killed off organisms that couldn't adapt. It forced life into new niches, away from the poison zones. There may have been brief moments, regional events, short-lived increases, when oxygen levels rose above the usual baseline. Enough to affect chemistry, but not enough to change the world. These were false starts, spikes, episodes that left traces in rock but didn't lead to lasting transformation. The system pushed back. The sinks were still too strong. The balance still tilted against accumulation. But something was shifting slowly and inexorably. The oxygen sinks were filling up. Iron concentrations in the ocean dropped. More banded iron formations formed, then declined. Methane levels, once stabilised by a haze-producing atmosphere, began to fall. Oxygen's influence crept outward, becoming harder to isolate to microenvironments. The stage was setting for a permanent change. That change wouldn't happen until well after the Archean, during the Paleo-Proterozoic, in what's known as the Great Oxidation Event. But the groundwork was all here. The microbes, the mats, the endless sunlight, the quiet, tireless leak of oxygen into a world not designed to handle it. And over time, that leak became a trickle. The trickle, a flow. Eventually the chemistry would break. The threshold would be crossed. What followed that crossing was not immediate explosion, but long, drawn-out transformation. Oxygen rose gradually, then in bursts, then settled into new equilibriums. The atmosphere changed, the biosphere reorganized. Entire groups of microbes disappeared, unable to survive in the new oxidizing world. Others took their place. Complexity became possible. But in the Archaean, that was all in the future. The weight was still on, and the world, strange and breathingless, went about its business. Volcanoes erupted, continents shifted, tides rose and fell. Life carried on, mostly unaware that it was reshaping the atmosphere, one molecule at a time. The long wait for oxygen was not a pause, it was a process. One that moved quietly in sunlight and sediment, in layers of microbial film, in the chemistry of seawater and the crust of the planet itself. And when it finally tipped, the world would never be the same again. It's a fair question. If you stand on a beach or hike a mountain trail, you're surrounded by things you can see and touch. Trees, rocks, animals, clouds. But the Archaean? That's so far back it's not just before people, it's before bones, before leaves, before shells, before the things that usually fossilise and fill museum drawers. So how do we know what Earth was like back then? What the atmosphere held, what the oceans were made of, what the land looked like, and what microbes were doing in the shallows? We know because the Earth remembers, even if it doesn't remember clearly. It keeps records in rock, not photographs, not narratives, just physical and chemical patterns left behind by ancient processes. And if you know how to read those patterns, you can reconstruct the world as it once was, not with certainty, but with enough clues to form a picture. The oldest pieces of the planet we still have are rocks, some of them over 4 billion years old, especially a kind called zircon, a durable mineral that forms in molten environments and can survive even when the rest of the rock has been destroyed. Zircons contain uranium, which decays into lead at known rate. By measuring how much lead has formed inside a zircon grain, scientists can determine its age, sometimes down to a window of a few million years, which is surprisingly precise when you're dealing with events more than 3 billion years ago. Some zircons are found inside younger rocks, which tells us not just how old the grains are, but what kind of environment they formed in. Their chemical composition contains hints of the water they crystallized in. Oxygen isotopes, for example, suggest liquid water existed on the surface of the planet as early as 4.3 billion years ago, even before the Archean began. Other rocks, especially banded iron formations, record the activity of oxygen in the ocean. These are sedimentary structures made of alternating layers of iron-rich minerals and silica. They only form under very specific chemical conditions, lots of dissolved iron in the ocean, and periodic exposure to oxygen. The oxygen would cause the iron to oxidize and fall out of solution, layering onto the sea floor. Then, when oxygen dropped again, the silica could settle. Layer after layer, this pattern repeated, and when we find banded iron formations in Archean rock, we're looking at the pulse of oxygen production and removal written directly into the seafloor. There are also isotopic fingerprints in ancient carbon. Life tends to prefer the lighter version of carbon, carbon-12, over the heavier carbon-13. When ancient microbes photosynthesized or metabolized carbon-based molecules, they left behind material enriched in carbon-12. These traces preserved in sediments suggest biological activity even in the absence of body fossils. When we analyse the carbon isotope ratios in rocks dated to more than 3.5 billion years ago, we find hints of life. Not life we can see, but life that left a chemical shadow. Sulfur isotopes also tell a story. In the Archaean, the atmosphere had little to no oxygen, and the way sulfur cycled through air and water was different. Volcanic gases release sulfur compounds into the atmosphere, and without oxygen they underwent unusual reactions driven by ultraviolet light. These reactions left behind distinct isotope ratios, called mass-independent fractionation, that only occur in an anoxic atmosphere. We find these signatures in Archean rocks, and when they disappear from the record it marks a shift, the rise of oxygen, a planetary chemical transition, visible only at the molecular level. In places like the Pilbara Craton in Australia or the Barberton Greenstone Belt in South Africa, we find well-preserved ancient sediments, folded, buried and metamorphosed, but still containing the basic structures of Earth's early surface. In some of these rocks we even find stromatolites, fossilized microbial mats that built themselves up in layers over time. These aren't fossils of the microbes themselves, but they're fossils of what the microbes built. Dome-like structures, laminated with growth rings, showing that life was actively shaping its environment. Even the absence of certain features tells us something. There are no animal fossils in Archean rocks, no plant impressions, no signs of oxygen-dependent minerals forming at the surface. That absence isn't a blank, it's a data point. It tells us what the Earth couldn't support yet. We also look at detrital minerals, grains of stable minerals like uraninite or pyrite that, in today's oxygen-rich world, would oxidize and disappear before they could be buried. In Archaean sediments, these minerals survived transport through rivers and streams because the atmosphere wasn't yet oxidizing. Their presence is a strong indicator that the air was low in oxygen at the time they were deposited. None of this is easy to read. These rocks are old, altered, fractured, and sometimes folded beyond recognition. The isotopic signatures can be subtle. The structures, ambiguous. It takes comparison, cross-checking, and often disagreement among scientists to build a coherent picture. And yet, over decades of work, that picture has come into focus. We don't see the Archaean directly. We see it refracted through the evidence it left behind, in mineral grains that remember their formation, in chemical ratios that preserve biological bias, in structures shaped not by organisms themselves, but by their behaviour, in sediments that still bear the influence of tides pulled by a closer moon. And that's how we know, not from stories, but from the physical consequences of what happened. The Earth, even at its most hostile and unrecognisable, still obeyed the rules of physics and chemistry. And it left behind a record, as long as you know how to look. It's not perfect. There are gaps. Whole continents have been subducted, cratons shattered, records erased. The Archaean is a partial archive, one that must be interpreted carefully, always with a margin of uncertainty. But it's enough to tell a story, not in full colour, not in sharp detail, but clearly enough that we can say, this is what it was probably like. This is what life was doing. This is how the world began to become itself. And in that story we find ourselves, not directly but distantly, because everything we are came from that quiet, deep, ancient world. The one with no breath, no trees, no fire, no sound, just rock, water, light, time, and the first stubborn signs of the life writing its story molecule by molecule into the only surface it had. By the time the Archean Eon gave way to the next, the Earth hadn't changed all at once. There was no sudden shift in colour, no line drawn across the crust. The rocks didn't notice, the microbes didn't hold their breath. The planet kept turning, just a little slower than before. The sun kept rising over oceans that still held no fish, and the air, still mostly unbreathable, had just the faintest trace of something new in it. This is how change really works on a planetary scale, quietly, gradually, with long periods of almost nothing, followed by brief pulses that never fully go back to how things were. The Archaean didn't end because it was over. It ended because the conditions that defined it, the chemistry, the heat, the crust, the atmosphere, the pace, slowly shifted until they were something else. Oxygen had begun to accumulate in places it couldn't before. The photosynthesizers were still working, same as ever, but the sinks were weakening. Iron was harder to find, sulfur was changing. The ocean and atmosphere were no longer able to hold oxygen down completely. And that one change would unlock everything that followed. The continents, once just scattered fragments of crust, had started to come together. Not full supercontinents, not yet, but assemblies, pieces of buoyant landmass that stuck around. They moved slowly, collided, deformed. Mountains rose, weathered, and eroded into rivers that carried minerals back into the sea. The cycle of rock had deepened, so had the cycle of life, and life, still microscopic, still invisible, was beginning to alter its surroundings in ways that left clearer traces, not just in banded iron or carbon isotopes, but in layers of organic material building up faster than before. Life was no longer just adapting to the Earth, it was shaping it. Even the sky was different now. The haze that once filled it, driven by methane and lack of oxygen, was thinning. Blue was starting to appear, faintly on certain days in certain places, not often, not everywhere, but enough. The sun, still dimmer than today's, was steady. The moon was slightly farther away, the tides a little calmer, the rotation a bit slower. The same forces still working, still softening the edges of a world that once knew only extremes. And through it all, the Earth kept remembering, layering stories into rock, holding heat in the core, tracing patterns of life in stone. It didn't know it was writing history, but it was. When we talk about the Archean, we're not talking about something gone. We're talking about the part of Earth that still lives in the deepest rocks, in the minerals that form the base of continents, in the legacy of microbes that still perform photosynthesis every day, in the oxygen we breathe, in the tilt of the Earth, stabilized by the moon that came from the impact before the Archean even began. We carry its history in our cells and in our sky. The Archean never really said goodbye. It just became the Proterozoic, a new eon with a new atmosphere, a new pace, and eventually new forms of life. But even then the foundation stayed the same. The continents were Archean at their core. The first steps toward complexity were built on Archean rules. The Earth was no longer young, but it wasn't old yet either. It was learning how to host life, not just tolerate it, but support it. And maybe that's the best way to describe what the Archean was. The time when Earth figured itself out. Not in any conscious way, not in a rush, but in long, slow processes that built toward everything else. Fire would come later, so would breathing, so would trees and fossils and animals with eyes. But none of that could happen until this part was finished, and now it is. So, if you've listened this far, whether lying in bed, walking under the stars, or drifting into sleep, thank you for slowing down, for being curious, for letting this story unfold the way the Earth did, steadily, patiently, and without the need for an ending. The Archean didn't have one, it just kept going, and so will we. Good night, Archean. Good night, Earth.